Each night, the moon quietly appears as though it has always belonged in our sky. But the more closely we look, the more its place there begins to feel like an almost impossible arrangement. You're listening to Night Cosmos Sleep. The moon is nearly 400 times smaller than the sun, while the sun is also almost exactly 400 times farther away. Because of this, the two bodies appear nearly the same size in our sky, creating total solar eclipses that fit together with remarkable precision. The moon always keeps nearly the same face turned toward Earth, pulling the oceans into their tides and slowly changing the rhythm of our planet's rotation. Is this simply a chain of natural coincidences unfolding over billions of years? Or does the moon conceal a different origin? To search for an answer, we should begin with its most familiar features, the things that seem perfectly ordinary, yet become increasingly difficult to explain the more closely we observe them. In the darkened room, a pale band of light slips through a gap in the curtains and rests quietly on the floor, gentle enough not to wake anyone, yet clear enough to remind us that beyond the window, a world is still moving in silence. That light comes from the moon, an object so familiar that we often see it without ever truly observing it. No one remembers the exact first moment they looked up and recognized the moon. It seems to have existed before memory itself, entering childhood through lullabies, ancient stories, and nights when an adult pointed toward the sky. Long before humans understood orbits or gravity, the moon was already part of everyday life. Its steady changes once helped many civilizations measure time. From the thin crescent at the beginning of a month to the bright disk of the full moon, each cycle became a natural calendar that anyone could see. People used it to track the seasons, organize ceremonies, and prepare for long journeys. For communities living near the sea, the moon was also connected to the rising and falling of the tides. Fishermen watched the sky to choose when to set out, while travelers made use of moonlit nights to move without carrying as many torches. A celestial body, hundreds of thousands of kilometers away, quietly became part of some of humanity's most ordinary decisions. In many Eastern cultures, the moon often evokes reunion, longing, and thoughts of those living far apart. The same moon can be seen from two distant places, turning it into a symbol of connection. Yet when moonlight falls across an empty courtyard, it can just as easily carry a sense of solitude. In many Western stories, the full moon appears beside dark forests, transformation, and the fear of forces beyond human control. Legends of creatures emerging under moonlight have survived for generations. The same celestial body has carried both tenderness and unease. Today, the moon is known through more than stories. Measurements show that its average distance from Earth is about 384,400 kilometers. Light takes only a little more than a second to cross that distance. But for the kinds of vehicles we use on the ground, it would still be an extraordinarily long journey. The moon is about 3,475 kilometers wide, nearly 27% of Earth's diameter. Its mass is only about 1/81st that of our planet. These numbers show that the moon is far smaller than Earth, yet it is not small at all compared with the planet it orbits. There are moons in the solar system larger than ours, but they usually orbit giant planets such as Jupiter or Saturn. Earth is only a moderately sized rocky planet. That makes its possession of a moon more than 1/4 its own diameter fairly unusual. The moon's average density is lower than Earth's, partly because its metallic core is smaller. Beneath the dusty, cratered surface are a crust, a mantle, and a core, much like the internal structure of a complete rocky world. It is not simply a cold lump of matter hanging beyond Earth. From the ground, the moon appears large and clear because it is so much closer to us than the stars. Most objects in the night sky appear only as points of light, while the moon can be seen as a round disk with distinct bright and dark regions. Even without a telescope, the naked eye can recognize broad features across its surface. Ancient observers once believed the dark regions were seas. The name Maria, meaning seas, is still used today, but they contain no water. They are plains of basaltic lava that cooled billions of years ago. Large impacts once carved deep basins into the lunar surface. Lava from the interior later rose and filled some of these depressions, forming the darker plains. Seen from Earth, they combine with the brighter highlands to create familiar patterns. Some people see a face in the lunar disk. Others recognize a rabbit, a seated figure, or images drawn from the legends of the places where they grew up. Those shapes are not truly there, but the human brain naturally searches for familiar forms in random patterns. This is also one reason the moon so easily becomes the starting point for mysterious stories. A dark region may resemble an entrance, a ridge may look like a wall, and the long shadow of a boulder can sometimes make it appear like a tower. When an image lacks detail, the mind often fills in what is missing. The moon's familiarity has also allowed many misconceptions to survive for a long time. It does not produce its own light. It only reflects light from the sunday. The dust and rock on its surface scatter a portion of that light back toward Earth, creating the soft glow we see at night. The phrase, "the dark side of the moon," is not entirely accurate either. The hemisphere that faces away from Earth still experiences day and night. It is illuminated by the sun and then passes into darkness. When we see a new moon, most of the far side is actually in daylight. The moon is not motionless, as many people once imagined. It rotates on its axis while also traveling around Earth. These two motions occur at nearly the same rate, causing almost the same hemisphere to remain turned toward us. Its orbit is not a perfect circle. The moon sometimes moves closer to Earth and sometimes farther away because its path is slightly elongated into an ellipse. As a result, the apparent size of the lunar disk changes subtly over time. Human beings do not see exactly half of the moon's surface either. Small changes in its orbit and our viewing angle make it appear to rock gently back and forth. Because of this motion, known as libration, we can observe nearly 59% of its surface in total. Even so, for most of human history, more than 40% remained completely hidden from view. No one on Earth knew what that region looked like until spacecraft flew around the far side in the 20th century. It was a world very close to us, yet nearly half of its face remained concealed for thousands of years. That absence left a wide space for imagination. Before clear images existed, every unusual patch of brightness or extended shadow could become evidence of something mysterious. Even after better photographs became available, changing angles of sunlight could still make the same landscape look entirely different. The moon's surface has almost no rain, rivers, or wind to quickly erase its features. Craters, cliffs, and lava plains can remain for immense spans of time. The entire surface is therefore like an ancient archive, preserving the history of impacts throughout the solar system. Near the polar regions, some deep craters never receive direct sunlight. Temperatures there are low enough for water ice to survive for millions or even billions of years. On a world that appears completely dry, these shadowed regions still preserve material that humans now hope to reach. The moon is therefore both familiar and strange. We can see it from a backyard, through a window, or while walking home at night. Yet beneath its quiet appearance is a world with a complex formation history, an internal structure of its own, and many regions that have never been explored directly. When these features are placed beside one another, questions begin to emerge. Why does Earth have such a relatively large moon? Why does the moon keep almost the same face turned toward us? And why are its two hemispheres so visibly different? These questions do not require a distant or extraordinary hypothesis. Most can be approached through gravity, geology, and the evolutionary history of the Earth-Moon system. Yet the very familiarity of the moon allowed these unusual features to be overlooked for a long time. The most intriguing coincidence appears only when the moon's size is compared with an object hundreds of times larger. In the sky, the lunar disk can pass directly in front of the sun, covering almost all of its light and turning daytime into a brief interval of darkness. The numbers we have considered so far only show that the moon is relatively large compared with Earth. The more astonishing coincidence is that such a small world can almost perfectly cover the enormous star that illuminates the entire solar system. The moon is already large enough to be an unusual satellite of Earth, but what makes its size seem truly remarkable only becomes apparent when it passes in front of the Sunday. In that moment, a small rocky world can almost perfectly cover a star hundreds of times larger. Daylight slowly fades, the temperature begins to fall, and a cold shadow spreads across the ground. The change does not happen all at once. During the first few minutes, the sky remains blue, and the landscape is still clearly visible. Yet the colors around us seem to lose their intensity. The light gradually gives up its familiar warmth, giving midday a quality unlike any ordinary sunset. Shadows on the ground become sharper. The air grows cooler, while some birds fall silent or begin returning to their nests. They respond to the fading light as though night has arrived many hours too early. The moon continues, sliding across the face of the Sunday. The remaining light narrows into a thin crescent, then disappears completely. The brightest planets and stars begin to emerge in the daytime sky, while the horizon takes on the colors of a sunset surrounding the observer in every direction. Only a black circle remains overhead, encircled by delicate streams of soft white light. This is the solar corona, the extremely hot outer atmosphere of the sun, normally hidden by the brilliant light of its surface. For a few brief minutes, the moon appears to fit the sun almost perfectly. It is not so small that sunlight spills widely around it, nor so large that it conceals the entire corona. The balance is precise enough to make it seem as though the two bodies were placed in exactly the right positions, but their true sizes are completely different. The sun is about 1.39 million kilometers in diameter, while the moon is only about 3,475 kilometers wide. If the two bodies were placed side by side, nearly 400 moons would have to be arranged across the sun to almost match its diameter. An object that small would seem incapable of covering such an enormous star. What makes the sight possible is not their true size, but their distances from an observer on Earth. The moon is, on average, about 384,400 kilometers away. The sun lies nearly 150 million kilometers from Earth. The sun is almost 400 times larger than the moon, but it is also nearly 400 times farther away. As a result, the two objects occupy almost the same amount of space in our field of view. This is known as apparent size, the size an object seems to have in the sky, rather than its actual physical dimensions. A coin held close to the eye can block a distant building, even though the building is vastly larger. The moon does something similar to the Sunday. It does not need to be as large as the star. It only needs to be close enough for its disk to appear nearly the same size. When the moon passes close to the line connecting Earth and the sun, its shadow falls across the planet's surface. People standing within the darkest part of that shadow can witness a total solar eclipse. In the surrounding regions, the moon covers only part of the Sunday. The path from which totality can be seen is usually very narrow. It travels across Earth along an extended track, leading many people to journey hundreds or even thousands of kilometers to stand in the right place at the right time. Moving only a short distance outside that path can dramatically change the experience. The sun does not disappear completely, and the uncovered portion remains bright enough to overwhelm the corona. A small distance on the ground can mean the difference between total darkness and a midday that merely grows slightly dimmer. Even within the path of totality, the fit is not always equally perfect. The moon's orbit around Earth is not a flawless circle, but an ellipse. The distance between the two worlds therefore changes continuously. When the moon is closer to Earth, it appears slightly larger. If it passes in front of the sun at that time, its disk can completely cover the bright solar surface, producing a total eclipse. When the moon is farther away, its apparent size becomes smaller. It may still pass directly across the center of the sun, but it is no longer large enough to conceal the entire star. A brilliant ring of light remains visible around the dark disk, creating an annular eclipse. That ring reveals that the ratio of nearly 400 to 1 is not a fixed or absolute arrangement. The distances are always changing, and so are the apparent sizes. Even the sun does not always appear exactly the same size in our sky, because Earth's orbit around it is also slightly elliptical. At certain times, the moon appears a little larger than the Sunday. At others, it appears smaller. Humanity happens to be living during an era when their apparent sizes are close enough for both total and annular eclipses to occur. The moon passes between Earth and the sun at every new moon. Yet eclipses do not happen every month because the moon's orbit does not lie precisely in the same plane as Earth's path around the Sunday. The two orbital planes are tilted by about 5 degrees. That may sound like a small angle, but across the vastness of space, it is enough to make the moon pass above or below the sun's disk most of the time, as seen from Earth. The moon's orbit crosses Earth's orbital plane at 2 points. An eclipse can occur only when the moon passes near one of these intersections at the same time that it lies between Earth and the Sunday. A solar eclipse, therefore, requires several conditions to come together. The moon must be in the correct phase and pass through the correct region of its orbit, while the observer must also stand directly within the path of the narrow shadow sweeping across the planet. This combination of precise position and timing makes a total solar eclipse a rare experience for any particular place. Across Earth as a whole, the phenomenon continues to occur in regular cycles, but a specific city may wait many generations before falling within the path of totality again. That rarity can make the event feel deliberately arranged. Yet the balance we see today has not existed throughout the entire history of the Earth-Moon system. In the distant past, the moon was much closer to Earth. It appeared larger in the sky and covered more of the sun than necessary. Ancient eclipses probably did not possess the same precise fit that people can witness today. The moon is still slowly moving away from us. Reflectors placed on its surface during the Apollo missions allow scientists to send laser pulses from Earth and measure how long the light takes to reach the moon and return. These measurements show that the average distance is increasing by about 3.8 centimeters each year. That is only a tiny change, roughly the length of a finger, and it cannot be detected by sight during a human lifetime. But over hundreds of millions of years, those small centimeters will accumulate into an enormous distance. As the moon moves farther away, its disk will gradually appear smaller in the sky. In the far future, it will no longer be large enough to completely cover the sun, even when it reaches the closest point in its orbit around Earth. Partial and annular eclipses will still occur, but total solar eclipses will eventually disappear. Generations living in that distant age will no longer see the corona surrounding a perfectly black disk. Daytime will no longer fall into darkness in the way people today can still experience. This makes our era unusual, not because the moon is standing still in some perfect position, but because it is passing through a temporary range of distances, where its apparent size is almost balanced with that of the Sunday. That balance did not exist from the beginning, and it will not last forever. It is only a brief window within the roughly 5 billion year history of the Earth-Moon system. Humanity happened to emerge within that window of time late enough that the moon no longer appeared overwhelmingly large in the sky, yet early enough that it had not moved so far away that it could no longer cover the sun completely. Not only do the two celestial bodies have nearly the same apparent size, but a species capable of observing, measuring, and asking questions also appeared at precisely the right time to recognize that balance. Still, a rare coincidence does not automatically become evidence of design. In a universe containing countless stars, planets, and moons, unusual configurations can still arise through natural processes. To demonstrate that the moon was artificially constructed, the precise fit seen during an eclipse would not be enough. There would need to be manufactured materials, signs of engineering, a mechanism capable of placing it into orbit, or structures that could not have formed through natural geological processes. So far, eclipses show only that the moon's present size and distance create an extraordinary phenomena. They do not reveal whether anyone ever placed the moon in that position, nor do they prove that such an arrangement ever took place. Even so, the scientific explanation does not make the sight any less strange. Knowing that the sun is nearly 400 times larger, but also nearly 400 times farther away, only makes the moment when the two disks overlap seem even more remarkable. An enormous star lies nearly 150 million kilometers from us. A small rocky satellite travels around Earth from the precise position occupied by humanity. They appear almost equal in size and create several minutes of darkness in the middle of the day. Distance can explain how the moon is able to cover the Sunday, but distance does not explain another familiar feature that has accompanied humanity for thousands of years. No matter where on Earth it is observed, or during which period of history, the moon has always kept nearly the same face turned toward our planet. Its shape changes from crescent to full, yet the familiar bright and dark regions never seem to truly rotate away. Distance can explain why the moon almost perfectly covers the Sunday, but it does not explain another feature that has remained before human eyes for thousands of years. Although the lunar disk changes from crescent to full, its familiar bright and dark regions almost never seem to turn away. This has led many people to believe that the moon does not rotate. It simply travels around Earth like an object that always keeps one side facing us. That idea seems reasonable, because from one night to the next, the familiar face on the lunar disk appears in nearly the same position. In reality, the moon does rotate on its axis. If it did not rotate at all, then during each orbit around Earth, we would gradually see different sides of it. The familiar dark regions would drift toward the edge, disappear, and later return from the opposite side. What makes the moon unusual is the timing of its motion. It takes about 27.3 days to complete one rotation on its axis, and nearly the same amount of time to orbit Earth when measured relative to the background stars. The two motions are synchronized so closely that the same hemisphere always remains turned toward our planet. This movement can be understood through a very simple example. Imagine someone standing in the middle of a room while you walk in a circle around them, always keeping your face turned toward that person. By the time you return to your starting point, you have not only completed one orbit around them, but also rotated once around your own axis. At the beginning, you are facing the person in the center. As you move to one side, you must turn your body by a quarter turn to keep looking at them. When you reach the opposite side, your back faces your original position, but your face is still directed toward the center. As you continue walking, your body turns farther until you return to where you began. Throughout the entire journey, the person in the middle sees only your front. Even so, you have not remained motionless. You have completed one full rotation. The moon moves according to the same principle. It travels around Earth while continuously rotating on its axis, but the rates of those two motions remain almost exactly matched. As a result, from our planet, the dark plains and bright highlands continue to form the same familiar face. This condition is called synchronous rotation, more commonly known as tidal locking. The word locking may suggest that the moon has been fixed in place, but there is no physical latch or invisible force holding it still. It is the result of gravity acting continuously over an immense span of time. The moon is not the only celestial body that moves in this way. Many of the large moons of Jupiter and Saturn always keep nearly the same hemisphere facing their parent planets. Worlds such as Io, Europa, Ganymede, and Titan have all entered a state of synchronous rotation. Far beyond the solar system, some planets orbiting very close to their stars may also be tidally locked. One side always faces the star and receives continuous light, while the other remains in an extended night. The temperature difference between the two hemispheres can shape the entire climate of those worlds. Tidal locking is therefore not a feature unique to the moon. It is an outcome that can arise whenever two celestial bodies exert a strong gravitational influence on each other for long enough. The question is not why the moon is being held in place, but how its original rotation slowed to the rhythm we see today. When the moon first formed, it probably rotated much faster. It was also much closer to Earth, making the gravitational interaction between the two worlds stronger than it is now. Earth's gravity did not pull equally on every part of the moon. The side facing Earth experienced a slightly stronger pull than the far side. This small difference stretched the moon very slightly, creating two bulges on opposite sides. One faced Earth, while the other formed on the opposite side. Rock may seem rigid, but on the scale of an entire celestial body, it can still deform. The change was far too small to see, yet large enough to affect the moon's rotation. When the moon was spinning faster, the bulges could not remain perfectly aligned with Earth. Whenever a bulge was pulled away from its balanced position, Earth's gravity acted to draw it back. This created resistance against the moon's rotation, much like a very gentle hand continuously slowing a spinning object. Inside the moon, rock bent and deformed through each cycle. Some of the energy of motion was converted into heat and then dissipated. The change during any single rotation was extremely small, but repeated over millions and billions of years, it was enough to gradually reduce the moon's spin. Eventually, the moon reached a state in which one rotation took nearly the same amount of time as one orbit around Earth. At that point, the bulges remained more stable in relation to our planet. Internal friction decreased greatly, and the system settled into a long-lasting rhythm. This was not a complete stop. The moon still rotates, still travels through space, and still responds to the gravity of Earth, the Sun, and other celestial bodies. Only its rotational period and orbital period have become matched in a remarkably stable ratio. Earth also experiences ocean tides because of the same difference in gravitational pull. But the moon has no vast oceans across its surface. Its tides mainly involve the extremely slight deformation of the entire rocky body, unfolding slowly and remaining almost impossible to notice by sight alone. The term tidal locking comes from this very process. The forces that create tides gradually adjusted the moon's rotation until its two motions settled into the same rhythm. There was no sudden arrangement, only gravity working patiently over a very long time. Even so, synchronous rotation created a remarkable boundary in human awareness. One side of the moon has always remained before us, while the other was once completely hidden from every person living on Earth. The hemisphere facing away from us is often called the dark side of the moon. That name can suggest a region forever trapped in darkness, cold and untouched by sunlight. In reality, the far side experiences both day and night, just like the near side. The moon does not produce its own light, so whichever part faces the sun becomes illuminated. When we see a full moon, the near side is almost entirely in daylight, while most of the far side is in darkness. When the moon is new, the situation is nearly reversed. At that time, the side facing Earth is in night and is almost invisible against the bright sky. Meanwhile, the far side is receiving sunlight. One half is still illuminated and the other remains dark. Only the boundary between them continues to move as the moon follows its orbit. The more accurate terms are the near side and the far side. The near side is the hemisphere that usually faces Earth, while the far side is the hemisphere that usually faces outward into space. Their distances from Earth are not dramatically different, but these names avoid the false impression that one side is always dark. For most of human history, no one knew what the far side looked like. No telescope, no matter how powerful, could see around a solid world. Humanity had to wait until a spacecraft could travel beyond the moon's edge and send images back. In 1959, the Soviet spacecraft Luna 3 flew around the far side of the moon. Its first photographs were blurry and primitive by modern standards, but they revealed a region of the lunar surface that no human eye had ever seen. What surprised scientists was not only that the far side had finally been revealed, it also looked distinctly different from the familiar face turned toward Earth. The broad, dark plains were nearly absent, replaced by brighter highlands and countless overlapping craters. Before exploring that difference more deeply, one detail still needs to be clarified. Although the moon keeps nearly the same side facing Earth, human observers are not limited to seeing exactly 50% of its surface. The moon's orbit is elliptical, so its orbital speed is not perfectly constant. When it is closer to Earth, it moves slightly faster. When it is farther away, it slows down, while its rotation on its axis remains more uniform. This slight difference makes the moon appear to rock gently from side to side. At times, we can see a little farther around its eastern edge, while at other times, a little more of the western edge comes into view. The moon's rotational axis is also slightly tilted relative to the plane of its orbit. As a result, over time, observers can see a little more of the region near the North Pole, and later, a little more near the South Pole. The entire motion resembles an extremely slow nodding and swaying across the sky. This phenomenon is called libration. The moon is not actually shaking dramatically in space. Instead, our viewing angle from Earth changes as it moves along its orbit. Because of this, over many months, humanity can observe nearly 59% of the lunar surface in total. At any single moment, we still see only about one hemisphere. But over time, regions near the edge gradually appear and then slip out of sight again. The portion that can never be seen from Earth is therefore slightly less than half of the surface. Even so, the remaining 40% once represented a complete blank space on humanity's maps. That absence gave rise to countless stories about what might be hidden beyond our view. When clearer images were finally sent back, the far side revealed no cities or enormous artificial structures, but it did reveal a genuine geological mystery. The two hemispheres of the same world seem to have experienced very different histories. The near side contains many dark regions known as Maria, formed when ancient lava flooded large impact basins. These basalt plains spread across the surface, creating the dark patches that can still be seen with the naked eye from Earth. The far side, however, has very few broad lava plains of this kind. Its surface is rougher, brighter, and far more densely covered in craters. Many regions still preserve ancient crust that was never buried beneath younger lava. One important reason lies in the thickness of the crust. Measurements show that the crust on the far side is generally thicker than on the near side. When major impacts occurred, molten material from the interior had more difficulty breaking through that thicker crust and reaching the surface. On the near side, the thinner crust made it easier for molten rock to rise. After large impacts, lava filled the basins and cooled into the broad, dark plains that remain visible today. But crustal thickness is not the only explanation. Heat-producing elements are also distributed unevenly between the two hemispheres. Some regions on the near side contain higher concentrations of uranium, thorium, and potassium, elements that can release heat through radioactive decay. That additional heat may have allowed volcanic activity to continue longer on the near side. The far side, meanwhile, cooled along a different path, preserving more ancient highlands and undergoing less volcanic resurfacing. Why these elements became so unevenly concentrated is still being studied. The asymmetry may have begun when the moon was still covered by a magma ocean. It is also possible that heat from the young Earth caused the two hemispheres to cool at different rates. When the moon first formed and remained much closer to Earth, our planet was far hotter than it is today. The side facing Earth may have received additional heat, causing its crust to form later or remain thinner. The far side, facing outward into space, may have cooled more quickly and developed a thicker crust. Later impacts continued to deepen the difference. A vast basin-forming collision could thin the crust on the near side and open pathways for lava to reach the surface. Each new event added another layer to an asymmetrical history that had begun very early. There is still no single explanation that fully accounts for every difference between the two hemispheres. Current models can describe parts of the process, but the exact origin of the contrast will require more rock samples and more data from regions that have not yet been explored directly. That gap in our knowledge is sometimes turned into the question of whether the far side was intentionally hidden. The fact that one hemisphere always faces away from Earth can create the impression that it is concealing something observers below were never meant to see. But tidal locking is a natural phenomenon found among many other moons. No observation device, guidance mechanism, or hidden hand is needed to keep the same side of the moon facing Earth. Gravity and time are enough to create this rhythm of motion. If the moon is a natural body formed early in the history of the solar system, synchronous rotation is exactly the kind of outcome we would expect. What remains incompletely explained is not why the moon keeps one side turned toward us. The deeper mystery lies in the history that caused the near and far sides to develop so differently. One hemisphere is covered with broad, dark lava plains, while the other preserves a thicker crust and a more ancient surface. It is one world with one origin, yet its two sides seem to hold two different geological stories. To understand how that difference arose, we must return to a time when the moon had not yet become the cold, rounded world we know today. The solar system was still chaotic. The young Earth rotated more rapidly, and growing worlds frequently collided with one another. The moon is not fixed in the sky like a camera, yet its present rotation, its asymmetrical crust, and its volcanic history all lead back to the same question: what created this world beside Earth? The answer may begin with a violent collision, when a body nearly the size of Mars struck the young Earth and threw material from both worlds into orbit. To understand why the moon's two hemispheres are so different, we have to return to a time before any craters, lava plains, or frozen polar regions existed. About 4.5 billion years ago, the moon had not yet formed, and Earth was not yet the calm blue world we know today. The sun had only recently emerged from an enormous cloud of gas and dust. Around it stretched a vast disk of material, where countless dust grains collided, stuck together, and gradually formed larger bodies of rock. Small fragments repeatedly merged, broke apart, and gathered again in a process that continued for millions of years. The early solar system did not yet have the stable orbits and familiar distances we see today. Many young celestial bodies moved around the sun, frequently crossing one another's paths. Some collisions only fractured their surfaces, but larger impacts could merge two worlds or almost completely destroy one of them. The young Earth was also built through this long sequence of collisions. Every rocky body that fell into it carried energy, heating and melting the surface. Heavy elements, such as iron, gradually sank inward to form the core, while lighter material rose toward the outside and created the mantle. A day on Earth was much shorter then than it is now. The planet rotated rapidly, its surface remained intensely hot, and stable oceans had not yet formed. Its early atmosphere was also completely different. While major impacts could still melt large portions of the surface all over again. Within this chaotic setting, the origin of the moon became a difficult question that challenged generations of scientists. Humanity knew that it was an unusually large satellite compared with Earth, but no one understood how such a world had come into existence. One early idea proposed that the moon had once been part of Earth. As the young planet spun rapidly, a large mass of material may have been thrown outward, leaving behind an enormous depression on the surface before gradually gathering into a satellite. This hypothesis was once appealing because it could explain the similarities between rocks from Earth and the Moon. If the two worlds had once been one, their compositions should naturally share many features. However, separating such a large portion of Earth would require a rotational speed and set of conditions that are difficult to reconcile with current models. Another hypothesis suggested that the Moon formed somewhere else in the solar system. After traveling independently for a long time, it passed close to Earth and was captured by the planet's gravity. It is not impossible for a planet to capture a smaller body. Many moons in the solar system may have experienced a similar history, but the Moon is massive, and its present orbit is relatively regular, making capture difficult to explain without some mechanism capable of removing an enormous amount of energy. A third possibility proposed that Earth and the Moon formed together from the same region of material. The two worlds grew beside one another from the beginning, sharing much of the same original matter, before gradually settling into a planet and moon system. This idea could explain their similar ages and compositions. But if both worlds formed in the same way, the Moon should contain a larger proportion of iron. In reality, its metallic core is much smaller than Earth's. Among the explanations that have been proposed, one model gradually gained more support than the others. The Moon may have been born from a colossal collision during the first few tens of millions of years in the history of the solar system. According to this model, the young Earth was not alone in its orbit. Another large body, roughly the size of Mars, was also traveling around the Sunday. This hypothetical world is commonly called Theia. Theia may not have struck Earth directly at its center. Many simulations suggest that an angled collision would be more consistent with the evidence. The two worlds approached at high speed, struck one another, and released enough energy to melt and vaporize an immense amount of rock. Most of Earth was not completely destroyed, but its surface may have become an ocean of molten stone. Material from Earth's outer layers and from Theia was thrown into space, forming a ring of debris around the planet. Seen from far away, the event would not have looked like a complete moon appearing all at once. Instead, billions of rock fragments, droplets of molten material, and silicate vapor surrounded Earth in a glowing disk. The fragments continued colliding with one another. Some broke into smaller pieces, while others joined together, and the largest bodies gradually pulled in more material through gravity. Over time, the disk of debris contracted and gathered into a single large world. On a cosmic timescale, this process may have happened very quickly. Some models suggest that much of the Moon could have formed within a period ranging from several months to a few years, although the full history of accretion and orbital stabilization would certainly have continued much longer. The early Moon was far closer to Earth than it is today. It would have appeared enormous in the young planet's sky, while the tidal forces between the two worlds were much stronger. Earth rotated rapidly, the Moon moved through a nearby orbit, and the entire system constantly exchanged energy. The newly formed Moon did not have the cold gray surface we see now. Energy from repeated collisions among the surrounding fragments kept much of the body molten. A deep magma ocean may have covered almost the entire surface. Within that ocean of molten rock, heavier minerals sank, while some lighter minerals gradually floated upward. Over time, they solidified and formed the first crust. The bright highlands, still visible today, may preserve ancient material from that early stage. Beneath the forming crust, the interior continued to cool very slowly. Heat-producing elements decayed, masses of material shifted, and new impacts continued to reshape the surface. The young Moon was still a highly active world, very different from the quiet body we see today. Evidence of this history is not found only in computer models. It is also preserved in the samples brought back to Earth by the Apollo astronauts. Between 1969 and 1972, 6 Apollo missions landed humans on the Moon. The astronauts collected rocks, soil, and fragments of material from several different regions and returned them to laboratories on Earth. The total mass of the collected samples was about 382 kilograms. For decades, those rocks have been studied with increasingly precise techniques. Even a tiny mineral grain can preserve information about temperature, age, and the environment in which it formed. One of the most significant findings is that the oxygen isotope composition of lunar rocks is remarkably similar to that of rocks on Earth. Oxygen exists in several isotopic forms, and the ratios between them often carry a distinctive signature of the region where a celestial body formed. Meteorites from Mars or other asteroids usually show clearly different isotopic patterns. Earth and the Moon, however, are so closely matched that scientists once struggled to explain the similarity if most of the Moon's material had come from an unfamiliar world. If Theia formed in a different region, its composition should have left a more obvious signature. The striking similarity between Earth and the Moon therefore supports the idea that they share material, while also creating a new problem for the impact model. Some simulations suggest that the collision may have been powerful enough to mix material from Earth and Theia almost completely. Other models propose that Theia may already have had a composition similar to Earth because both bodies formed in the same region of the solar system. There are also scenarios in which Earth once rotated much faster, allowing the collision to produce an enormous structure of vaporized rock around the planet. The Moon then condensed from material that had been thoroughly mixed within that structure. Each explanation attempts to solve the same question. How could a collision between two different celestial bodies produce a moon whose composition is so similar to Earth's? The Apollo samples also show that the Moon once experienced extremely high temperatures. Some rocks formed as magma cooled slowly, while other minerals suggest that the earliest crust once floated upon a deep and widespread ocean of molten rock. The Moon is also depleted in many volatile elements compared with Earth. These substances escape more easily at high temperatures. Their scarcity is consistent with a violent formation process in which material was heated, vaporized, and exposed directly to space. Later studies, however, also discovered water and other volatile substances within lunar rocks. This suggests that the Moon's thermal history was more complex than the image of a world baked completely dry. Some water may have survived the collision. More may have arrived later aboard meteorites and comets. Permanently cold regions near the poles still preserve water ice, raising further questions about when this material arrived and where it came from. The ages of the rock samples also gave rise to another misunderstanding. Some lunar rocks are older than nearly every type of rock still found on Earth's surface. This has sometimes been interpreted as evidence that the Moon must have formed before our planet. But ancient rocks do not necessarily mean an older celestial body. Earth has oceans, rain, wind, volcanoes, and plate tectonics. Its crust is continuously broken apart, drawn downward, melted, and remade into new rock. Much of the evidence from Earth's earliest history has been erased or buried deep below the surface. Rocks more than 4 billion years old are extremely rare, not because Earth is younger, but because its surface has never stopped changing. The Moon is different. It has no oceans or active system of plate tectonics like Earth. After volcanic activity weakened, many regions remained almost unchanged for billions of years. Aside from impacts that continued to form new craters, the lunar surface is therefore like an ancient archive. It preserves material from an era that Earth has almost completely erased from its own surface. The Moon's internal structure provides additional evidence. Earth has a large iron core that accounts for a significant part of its radius and mass. While the young planet was still molten, iron and other heavy elements sank inward and formed that core. The Moon's core is much smaller. This is consistent with the idea that most of the material that formed it came from the outer layers of Earth and Theia, which contained more silicate rock than iron. During the collision, Theia's metallic core may have merged with Earth's core, or remained deep inside the planet. The material thrown into orbit came mainly from the mantles, leaving the newly formed moon relatively poor in iron. These pieces create a fairly consistent story. A high-temperature collision explains the magma ocean, the loss of volatile substances, and the small core. Material drawn from Earth's outer layers helps explain the similarity between rocks from the two worlds, but the story is still incomplete. Scientists do not know exactly how large Theia was, how fast it was moving, or the angle at which it struck Earth. Even a small change in the initial conditions could produce a moon with a completely different mass, orbit, or composition. The proportion of material contributed by Earth and Theia also remains uncertain. Some models produce a moon formed mostly from Theia, while the isotopic evidence suggests either a major contribution from Earth or extensive mixing between both sources. There is no single accepted timescale for the moon's formation either. Most of its material may have gathered very quickly, but the magma ocean would have required much longer to cool. The earliest crust formed was broken apart by impacts and was rebuilt through several stages. The moon's original orbit is another part of the puzzle. It was once much closer to Earth, but exactly how close depends on the model. From that early orbit, tidal forces gradually pushed the moon outward and slowed Earth's rotation. The difference between the near and far sides cannot be fully explained by the collision alone. The crusts of the two hemispheres may have begun developing differently as the magma ocean cooled, but later impacts and volcanic activity made their histories even more complex. A theory that still lacks certain details does not mean every alternative hypothesis deserves equal weight. The giant impact model is supported because several independent lines of evidence point toward it. The composition of the rocks, the small core, signs of extensive melting, the depletion of volatile substances, and the motion of the Earth-Moon system. The idea that the moon is an artificial structure would require an entirely different kind of evidence. It would need to reveal manufactured materials, signs of engineering, structures that could not form naturally, or a mechanism capable of placing such an enormous body into orbit. So far, the available data fit more closely with a rocky world born during the chaotic early history of the solar system. Yet a natural origin does not make the moon any less mysterious. The Apollo samples came only from the near side, and from a limited number of regions. The far side, the polar areas, and material buried deep below the surface have not yet been fully sampled. Every new mission may add another piece to the puzzle, or force current models to change. Perhaps the moon formed after a single enormous collision, or perhaps the process unfolded through several more complicated stages, with material mixing, vaporizing, condensing, and gathering again over a period that has not yet been clearly determined. What is more certain is that the moon did not begin as the cold and silent world we see today. It was once molten, much closer to Earth, covered in magma, and repeatedly struck by violent impacts. After billions of years of cooling, its crust still preserves vibrations that humanity only began to hear after placing instruments on the surface. If the moon formed from molten rock and debris thrown outward by a colossal collision, why did falling Apollo rocket stages and equipment make it vibrate for so long that some people compared the entire world to a giant bell? If the moon formed from molten rock and debris thrown outward by a colossal collision, its interior should carry the structure of a natural rocky world. But when the Apollo instruments began recording vibrations across the surface, an unusual phenomenon led many people to ask an entirely different question. The astronauts did more than bring lunar rocks back to Earth. They also placed seismometers on the gray dust, allowing scientists to detect movements far too subtle for the human body to feel. These instruments did not record sound in the way a microphone does. They measured the movement of the ground when meteorites struck, when rocks fractured under changing temperatures, or when stress was released deep inside the moon. Over years of operation, the seismic network recorded thousands of different events. A world once thought to be completely silent turned out to have its own moonquakes, occurring at different depths and arising from several different causes. To study the interior, scientists needed vibrations whose locations and starting times were already known. Natural meteorites fall unpredictably, but spent rocket stages and modules that had completed their missions could be deliberately sent crashing into carefully calculated areas. The mass of each object, its speed, and the location of impact were estimated in advance. As the resulting seismic waves traveled through the moon and reached the monitoring stations, the way they moved could reveal layers of material hidden deep beneath the surface. Some of these impacts produced signals that lasted far longer than many people expected. Strong vibrations could continue for tens of minutes, while weaker motion remained detectable long after the object had come to rest. This gave rise to the description of the moon ringing like a bell. The comparison easily captures the imagination. A bell has a rigid shell surrounding an empty interior, and when struck, the entire structure continues to resonate. If the moon also vibrated for a long time, could its interior contain an enormous hollow chamber? The hollow moon hypothesis gradually grew from that question. Some interpretations went even further, suggesting that the surface rock might be only a covering, with a metallic shell or an ancient engineered structure hidden beneath it. But the phrase, ringing like a bell, describes only the long duration of the signal. It does not mean that scientists heard metallic sounds echoing from inside the moon. The lunar surface has almost no atmosphere to carry sound to the human ear. What the seismometers recorded was the movement of rock, which was then converted into electrical signals and transmitted back to Earth for analysis. When those signals are translated into sound, people can hear them as long, fading echoes. But that sound is only a way of representing the data, not an actual noise traveling through the air on the moon. The reason the vibrations lasted so long lies in the history of the crust itself. For billions of years, the moon was repeatedly struck by meteorites and asteroids. These impacts did more than create craters on the surface. They also shattered the rock below into countless fractured blocks. On Earth, water can seep into cracks. Minerals crystallize. Heat and pressure transform the rock, and ongoing geological activity continually reshapes the layers beneath the surface. The moon is far drier and has almost none of these powerful repair processes. Fractures created in the distant past may still remain today. When an impact occurs, seismic waves do not travel cleanly through one continuous mass of rock. They encounter countless cracks, boundaries, and broken blocks, causing them to reflect, change direction, and scatter. Some waves reach the instruments by a short path. Others pass through many layers of rock, changing direction repeatedly before arriving later. The signal, therefore, does not end all at once, but fades gradually through a long trailing sequence. The vibrational energy also diminishes slowly because the moon contains little water or soft material capable of absorbing it quickly. A solid rocky body can still vibrate for a long time if its interior is dry and heavily fractured. This makes the moon different from Earth. An earthquake on our planet usually travels through layers containing more water, altered minerals, and complex geological structures, all of which help disperse the energy more quickly. On the moon, the vibrations become trapped within a maze of shattered rock. The image of a ringing bell may therefore be accurate as an impression, but it is not evidence that the interior is hollow. The deliberate spacecraft impacts were not the only sources of vibration. The Apollo seismometers detected several types of moonquakes, and each revealed a different part of the world below. One group originated deep within the mantle. These events were usually small and repeatedly occurred in certain regions, following a rhythm connected to the moon's motion around Earth. Earth's gravity causes the entire moon to deform very slightly. Because the distance between the two worlds changes during each orbit, the gravitational pull also rises and falls, allowing stress to build and then release within the deep rock. This can be understood as a kind of tide occurring inside a solid world. Earth's oceans bulge under the influence of the moon, while rock deep within the moon is also pulled and flexed by Earth in an extremely slow rhythm. Another group consists of shallow moonquakes. These occur closer to the surface, are less common, but but can sometimes be significantly stronger and may continue for several minutes. These quakes may be connected to the fact that the moon is still cooling. As its interior loses heat, its volume decreases very slowly. The rigid outer crust cannot contract smoothly, so it becomes compressed, fractures, and slips along faults. Meteorites also continually produce vibrations. Because the moon does not have a thick enough atmosphere, even relatively small objects can strike the surface directly instead of burning up before reaching the ground. Each impact sends a new wave of energy into the crust. Some are strong enough to be detected by several stations, allowing scientists to locate the event and study how the energy travels. Near the surface, another form of vibration is caused by temperature. Both day and night last for a very long time on the moon, exposing the rocks to extreme thermal changes. When sunlight returns after a long lunar night, the surface heats up and expands. When darkness falls again, the rock cools and contracts. Repeated over time, this process creates countless small fractures and weak seismic signals. A world that appears dead is therefore still filled with movement. Earth pulls on its deep interior, the crust contracts, temperature changes make the rocks expand and shrink, and meteorites continue to strike the surface. By analyzing these vibrations, scientists can look inside the moon without drilling through hundreds of kilometers of rock. Seismic waves change speed as they pass through different materials. They can bend at the boundaries between layers, reflect back toward the surface, or weaken when they encounter regions that are hotter and softer. When several stations record the same event, differences in arrival times help reveal the paths taken by the waves. As thousands of events are layered together, they gradually create an indirect model of the lunar interior. The Apollo seismic data still have limitations. All the stations were located on the near side and concentrated within a relatively narrow region, while the heavily fractured crust caused many signals to scatter strongly. For that reason, scientists do not rely on moonquakes alone. They also measure the gravitational field, track subtle variations in the moon's rotation, and observe changes in the velocity of orbiting spacecraft. When a spacecraft passes over a region containing more mass, gravity pulls it forward by an extremely small amount. Changes in its radio signal allow scientists to map the mass hidden beneath the surface. Laser measurements from Earth also track the moon's motion with great precision. Tiny variations in its orientation reveal that the interior is not completely rigid, like a single unbroken mass of rock. When all of these observations are combined, a layered structure begins to emerge. At the outside is a rocky crust whose thickness varies between the near and far sides. Beneath it lies the mantle, which occupies most of the moon's volume and preserves traces of the ancient magma ocean. Deeper still, there may be a region of hotter, softer rock where some material remains partially molten. Seismic waves travel through this zone differently than they do through the colder rock above. At the center is a small iron-rich core. Its deepest part may be solid, while the surrounding layer may still contain liquid or partially molten material. The exact size, temperature, and composition of the core are still being studied, but the overall structure matches that of a rocky world with a crust, mantle, and core, not a sphere made only of an outer shell surrounding empty space. If the moon were truly hollow on a large scale, many measurements would produce completely different results. Its total mass would be lower. Its average density would not match the observed value. Surface gravity and the moon's gravitational influence on Earth would also be different. The distribution of mass affects how a celestial body rotates and responds to forces from outside. A hollow sphere with most of its mass concentrated near the surface would wobble differently from a world whose mass is distributed throughout its mantle and core. Seismic waves would also leave unmistakable signs if they encountered an enormous empty cavity. Strong reflections from the cavity boundary would repeatedly appear in the data, rather than the paths expected from several different layers of rock. The orbits of lunar spacecraft are also inconsistent, with a heavy shell surrounding a vast empty interior. Many independent measurements show that the moon's mass is distributed from the surface deep into its interior. Even so, its gravitational field is not perfectly uniform. Some large basins exert a stronger gravitational pull than the surrounding terrain. These regions are called mascons, short for mass concentrations. Before mascons were properly understood, they caused the orbits of low-flying lunar spacecraft to change in unexpected ways. A path that appeared stable could gradually be pulled off course with every orbit. This can create the impression that unusual masses are hidden beneath the surface. But the data show that mascons are usually located beneath large impact basins. When an enormous body struck the moon, it excavated the crust, and denser material from the mantle could rise closer to the surface. Basaltic lava later flooded the basin, adding even more mass. The combination of uplifted mantle material, deformed crust, and dense lava created regions with stronger gravity. Mascons are therefore records of impacts and geological activity, not evidence that all of the moon's mass is contained within an artificial shell. While orbiting spacecraft measure gravity from above, small cliffs on the surface reveal that another change is still taking place. The moon has been losing heat since it first formed. As its interior cools, the entire body contracts very slowly. The change is far too small to notice within a human lifetime, but it is enough to compress and fracture the brittle crust. Some sections of crust are pushed over others, forming long fault scarps across the surface. Several of these scarps cut through relatively young terrain, showing that they are not motionless remnants from the moon's earliest history. Some shallow moonquakes may be connected to faults that are still under stress. This means the moon has not become completely inactive in geological terms. There are no large tectonic plates moving as they do on Earth. No broad rivers of lava are flowing across the surface, but deep below, heat continues to escape, and the crust must still adjust to that slow contraction. The deliberate impacts during the Apollo era, therefore, did not reveal a vast hollow chamber. They revealed an extremely dry moon with a deeply fractured crust that retains seismic energy much longer than Earth does. The image of the moon, ringing like a bell, remains powerfully evocative. But that bell does not require an artificial void. Billions of fractures in the rock are enough to make seismic waves reflect, scatter, and fade slowly over many minutes or even hours. The available data fit more closely with a world containing a crust, a mantle, a partially molten region, and a small core at its center. Yet the surface above that structure still contains many shapes capable of stirring the imagination. There are craters that are wide but not as deep as a simple ratio might suggest, regions rich in titanium and uranium, and shadows that have sometimes resembled towers, walls, or machinery. If the moon's interior is not an artificial hollow chamber, could the features across its crust tell a different story? Or are they simply the products of impacts, lava, and shifting light on a world with almost no weather to erase its past? Seismic data does not reveal an enormous hollow chamber beneath the moon's surface, yet the crust above still preserves countless features capable of carrying the imagination far beyond the evidence. Unusually broad craters, regions rich in metals, and shadows that have been interpreted as towers, walls, or machinery. On Earth, most natural traces do not survive forever. Rain softens the ground, rivers carve valleys, wind wears away stone, and vegetation gradually covers places that were once destroyed. Even a large crater can become distorted and fade with time. The moon has almost none of these processes. The layer of gas surrounding it is far too thin to produce rain, wind, or weather in the familiar sense. No rivers cross the surface, no oceans fill the lowlands, and no forests grow to conceal the terrain. A mark created on the moon can therefore remain for an immense span of time. Craters formed billions of years ago are still clearly visible, overlapping one another like circles pressed into gray dust. The surface has become an almost untouched archive of the solar system's history of collisions. Every crater is the trace of an object that once struck at tremendous speed. In space, without a thick atmosphere to slow it down, even a small meteorite can hit the ground many times faster than a bullet. The energy of the impact compresses and heats the rock within an extremely short interval. Material is thrown high above the surface, some of it melts, while the layers below are crushed and then rebound. These processes occur almost simultaneously, producing a shape far more complex than a simple hole dug into the ground. Small craters usually resemble bowls. Their walls slope down toward the floor, while ejected material forms a raised rim around the outside. As a crater grows larger, however, that structure can no longer preserve the same proportions. During major impacts, the crater walls become too high and steep to remain stable. Rock begins to collapse and slide inward, widening the floor. The center may rebound upward, forming a mountain peak or a cluster of peaks in the middle. Some enormous basins are also filled with molten rock immediately after the impact. Liquid material flows into the lowest areas, cools, and creates a relatively flat floor. Later, lava from deeper within the moon may rise and cover the basin with yet another layer. For this reason, a crater many times wider does not necessarily become deeper by the same proportion. As its size increases, the collapse of the walls, the upward rebound of rock, and the filling of the floor with molten material transform its entire shape. If we imagine only an object driving straight down into soil and rock, large craters may appear shallower than expected. This has led to the idea that meteorites struck a hard layer beneath the surface, much like a drill hitting a sheet of metal it cannot penetrate. According to that interpretation, the dust and rock at the surface are only a covering. Deeper below, there could be an artificial rigid shell, strong enough to prevent objects from traveling farther down and limiting the depth of the craters. But impact geology does not work like dropping a stone into mud. At cosmic speeds, both the incoming object and the rock below are compressed, shattered, and melted. The final crater does not simply record how far the object penetrated. Many large craters may initially have been deeper than they appear today. After the impact, the walls collapsed, the floor rebounded, molten material flowed back inside, and later lava added additional layers. Each of these processes reduced the final depth. No metallic armor is needed to produce this effect. Craters with similar shapes also appear on Mercury, Mars, and other rocky moons, where impacts follow the same laws of physics. Large basins also created one of the most familiar features visible from Earth: the dark patches across the face of the moon. Ancient observers called them seas because their dark, relatively smooth surfaces resembled broad bodies of water. That name survives in astronomy through the word Maria. But there are no waves within these seas, no liquid water, and no coastlines like those on Earth. They are ancient impact basins later filled with basaltic lava. The lava is darker than the surrounding highlands, so from a distance, it forms patches large enough to be seen with the naked eye. Most of these dark plains lie on the near side. This is one reason the hemisphere facing Earth forms such a familiar face, while the far side appears brighter and is densely covered with highlands and craters. The dark regions have sometimes been interpreted as open entrances, exposed metal, or sheets of material laid across the surface. Spectral analysis, however, shows that they are consistent with basalt formed from ancient lava. Basalt is not an unfamiliar substance. On Earth, it is found across the ocean floor, around volcanic regions, and wherever lava once cooled. The difference is that on the moon, these plains have not been destroyed by water or tectonic activity. In some regions, lunar basalt contains relatively high amounts of titanium. This is often described as unusual because titanium is also used by humans in aircraft, rockets, and space equipment. Titanium is lighter than many other metals, Yet it is strong, heat-resistant, and highly resistant to corrosion. These qualities make it valuable in modern engineering, but the fact that humans use titanium does not mean every place containing it was manufactured. Titanium is a natural element. It formed before Earth or the Moon existed and is found in many minerals. On the Moon, it commonly occurs in ilmenite, combined with iron and oxygen. The important distinction is between a natural element and a manufactured alloy. Titanium contained within rock is not the same as a refined metal sheet that has been cast, shaped, or assembled into a structure. To demonstrate that a material is artificial, scientists would need to find signs of metallurgy, deliberately selected alloy ratios, machined surfaces, or arrangements that could not form naturally within magma. The mere presence of titanium satisfies none of these conditions. Titanium-rich regions are still scientifically important. They help reveal the Moon's volcanic history, the temperature of ancient magma, and the distribution of material within the interior. In the future, they may also become resources for long-duration missions. Another group of elements often mentioned in mysterious accounts includes uranium, thorium, and potassium. Because they are radioactive, their presence is sometimes linked to reactors, power sources, or technological systems hidden deep below the surface. But these elements also occur naturally in the rocks of many worlds. On Earth, uranium and thorium are scattered throughout the crust, and their decay contributes to the heat inside the planet. The Moon also carried small amounts of these elements from the time it formed. They are not evenly distributed, but are more concentrated in certain regions of the near side, especially around areas that once experienced intense volcanic activity. As uranium, thorium, and potassium decay, they release heat very slowly. This source of heat may have allowed parts of the interior to remain warm for longer, helping magma survive and continue rising toward the surface. The concentration of radioactive elements may therefore help explain why the near side contains more lava plains than the far side. It reveals part of the Moon's thermal history, but it does not yet indicate an artificial reactor. A manufactured reactor would require structures, processed materials, and a distinctive distribution of isotopes. Simply detecting uranium in natural rock is not very different from finding uranium ore on Earth. Alongside craters and metals, some of the most visually striking claims come from photographs. In many lunar images, viewers have identified objects resembling tall towers, bridges, walls, domes, or lines that appear almost perfectly perpendicular. Some shapes look so clear that it can be difficult to believe they are only rocks. One object may cast a long shadow across the ground, making its apparent height seem greater than any natural structure nearby. However, the length of a shadow does not depend only on the height of the object. It also changes with the angle of the light. When the sun sits very low on the horizon, even a small rock can cast a shadow dozens of times longer than its actual size. On the Moon, the sun moves very slowly across the sky. Near lunar sunrise or sunset, its light passes almost horizontally over the surface, making every ridge, boulder, and crater rim appear taller and sharper than usual. An object only a few meters high can resemble a tower when there are no trees, buildings, or people nearby to provide a sense of scale. In images taken from orbit, distance and size are difficult to judge without topographic data. Early space photographs also had limited resolution. A single pixel could represent a broad area of terrain, causing many small details to blend together. Natural boundaries could therefore appear straighter or more angular than they truly were. Dust on film, scratches, scanning errors, and interference during data transmission could also create bright points, dark streaks, or straight lines. As an image was copied repeatedly, each new generation could erase genuine detail while making visual defects more prominent. A straight line visible in only one copy could be mistaken for an object on the surface. When the original image or photographs taken from another angle were examined, the supposed structure sometimes disappeared completely. The human brain also plays an important role. We can recognize faces, human figures, and familiar objects from only a few lines or shapes. This ability is extremely useful in everyday life, but it can also give meaning to random patterns that do not truly contain it. A cluster of rocks can become a building. 3 nearby dark spots can become a face. 2 ridges crossing one another can make the viewer see a deliberately constructed right angle. This does not mean the observer is careless. It simply reflects the way the mind processes incomplete information. When a blurred image does not clearly reveal what an object is, the brain often chooses an interpretation that resembles something it already knows. A single photograph is not enough to confirm a real structure. The object would need to be photographed from several angles, at different times, and under different lighting conditions. If it were a tall structure, its shadow would have to change in a way consistent with the sun's position. If it were a wall, elevation data would need to show that the surface actually rises, rather than appearing only as a bright or dark line in an image. Modern orbiters can use lasers to measure the distance to the surface and create 3-dimensional topographic maps. Because this method does not depend entirely on visible light, it helps distinguish a real rock formation from a shadow or an imaging error. Spectral analysis can also reveal how an object absorbs and reflects light. A manufactured metallic structure would produce a different signature from lunar soil, basalt, or natural minerals. A large construction would also have to appear in data collected by multiple spacecraft. The moon has been observed by missions from many countries and agencies. A genuine object could not appear in only one old photograph and then vanish from every later dataset. Straight lines and nearly square angles are not sufficient evidence either. Nature can produce highly regular structures, from crystals and volcanic columns to fractures that follow weaknesses in the crust. On the moon, impact forces, thermal stress, and the contraction of the entire body can create long grooves, fault scarps, and intersecting lines that meet at nearly right angle. A shape may look artificial while still arising from natural physics. Although many supposed structures in lunar photographs have reasonable explanations, the moon's surface still contains real natural formations worth exploring. Among them are lava tubes hidden beneath the rock and soil. As lava flows across the surface, its outer layer can cool first and form a hard shell. The molten material inside continues moving, leaving behind an empty tunnel after the liquid drains away. If part of the roof collapses, a deep pit appears on the surface. These openings may lead into caverns extending for kilometers, shielded from radiation, small meteorites, and extreme temperature changes. From orbit, a pitch-black collapse pit can resemble a constructed entrance, yet naturally formed lava tubes have been observed in many volcanic regions on Earth and are expected to exist on other worlds with histories of volcanic activity. These caves may someday provide shelter for future explorers. Inside them, humans could be protected far more effectively than in structures built directly on the exposed surface. Near the 2 poles are regions of permanent shadow. Some deep craters sit at angles where sunlight never reaches the floor, even though their rims may remain illuminated for long periods. Temperatures there are low enough for water ice and many volatile substances to survive for immense spans of time. The dark soil may preserve material delivered by comets and meteorites, or released from within the moon itself. These areas have not yet been fully explored at close range. The darkness makes ordinary cameras less effective, while the difficult terrain complicates both landing and movement. Beneath the large basins, gravitational anomalies also remain imperfectly understood. The mass cons have been mapped, but the deeper distribution of material and the formation history of each region are still being studied. Examining unusual images is therefore not pointless. An object that resembles a structure may turn out to be only rock, but the effort to verify it may still lead to the discovery of a collapse pit, a fault scarp, or a geological feature that had never been recognized before. The boundary that must remain clear is the one between the unknown and the artificial. An unidentified shape does not automatically become machinery. A metal-rich region does not automatically consist of manufactured material. A shallow crater does not automatically prove that a rigid shell lies beneath it. Unknown means only that the available data is not yet sufficient for a confident conclusion. It is the beginning of measurement, not complete evidence for any particular hypothesis. Yet the mystery of the moon was not created only by blurred photographs. Long before humans had cameras, orbiters, or instruments capable of mapping terrain, many civilizations told strange stories about the origin of the glowing body in the sky. Craters, metals, and shadows can be tested through geology and modern data. But what happens when the idea that the moon was once brought to Earth does not come from a photograph, but is said to have survived within the ancient memories of many peoples? Was there truly an age when humans lived beneath a sky without the moon? Or were those stories simply the way ancient people spoke about a past so distant that no one could remember it clearly? The shapes found across the moon's surface can be examined through photographs, topographic maps, and mineral composition. But another group of stories is far more difficult to measure, because they are preserved not in rocks or radio signals, but in the language of civilizations that vanished long ago. In many parts of the world, people once spoke of a distant age, when the sky was different from the one we know today. Some stories describe a time before the moon appeared. Others say it was born, placed in the heavens, or became visible only after a flood that transformed the entire world. Viewed through a modern lens, these images can lead to an intriguing hypothesis. Perhaps the moon did not always orbit Earth. It may have appeared much later, when humans or their ancestors were already advanced enough to remember the change in the sky. One of the most frequently cited examples comes from the region of Arcadia in ancient Greece. In the Argonautica, composed around the 3rd century BCE, the Arcadians are described as having lived before the moon. This disputed phrase was therefore recorded more than 2,200 years ago. Taken entirely literally, the passage seems to claim that the ancestors of the Arcadians once lived beneath a sky without the familiar satellite. The moon appeared only later, after their community had already existed on Earth. This interpretation is often presented as evidence that ancient people preserved a memory of the moon being placed into orbit. But in the language of mythology, a phrase such as "before the moon" does not necessarily record an astronomical event. It may simply be a way of claiming that a people were so ancient that no one could remember their beginning. In many traditions, the ancestors of a community are described as existing before the mountains, before the sea, or from the very moment the world was created. Such statements are not intended to measure the true ages of mountains, oceans, or the moon. They emphasize antiquity, sacred status, and a community's deep connection to the land it inhabits. Before the moon might also mean before a lunar calendar was adopted, before the rise of a religion centered on the moon, or before an era named after a deity associated with that celestial body. After hundreds or thousands of years of copying and translation, the original context may gradually disappear. An image once used to express great antiquity can eventually be read as a literal claim that the moon was once absent from the sky. Similar stories are also said to exist in South America. Some modern retellings describe communities living in an age before the moon, or claim that the satellite appeared only after a great catastrophe. However, the versions circulating today have often passed through many layers of oral tradition, documentation, and translation. Not every story repeated in modern books and articles can be traced intact to a clear ancient source. An age without light at night may be reinterpreted as an age without the moon. A god who carries light into the sky may become someone placing a satellite into orbit. A change in calendars or rituals may be understood as the appearance of a new celestial body. In some regions of Africa, stories are also told in which the moon is created, thrown into the sky, or placed in its present position by a powerful being. In their traditional context, these stories may explain moonlight, the lunar phases, or the repeating cycle of appearance and disappearance. But when such stories enter the age of rockets, their meaning begins to change. A god who raises a shining object into the heavens can easily be reinterpreted as an advanced civilization. A divine vessel becomes a spacecraft, while a cosmic egg becomes a hollow structure. Every era tends to view the past through the objects most familiar to its own time. Ancient people explained thunder through gods, while those living among machines are more likely to recognize engines, technology, and extraterrestrials within mythological imagery. This does not mean that every legend is entirely fictional. It only shows that a story can change meaning as it passes through different storytellers and generations. One person alters a detail to make the story easier to understand. The next storyteller preserves that change and adds another image. After hundreds of years, the final version may be very different from the original event or meaning. The moon is especially suited to this kind of storytelling because its shape is always changing. It disappears during the new moon, returns as a thin line of light, grows into a full moon, and then gradually narrows again. One complete cycle lasts nearly a month. To people who did not understand orbital motion or reflected sunlight, the moon may have seemed like an object that repeatedly died and was born again. A legend describing the creation of the moon may simply have been intended to explain its return after several dark nights. A story in which the moon was removed from the sky may have begun with an eclipse, when the familiar bright disk suddenly changed color or vanished into shadow. But suppose these stories truly described an era only a few thousand or tens of thousands of years ago, when the moon had not yet entered its present orbit. Its arrival would then have been one of the greatest events in the entire history of the planet. The moon is not a small object that could quietly approach without leaving a trace. It is thousands of kilometers wide and massive enough to affect the oceans, Earth's crust, and the planet's rate of rotation. If an object like the moon approached from space and was then captured, an enormous amount of energy would have to be removed. Even a small error in its speed or direction could cause it to collide with Earth, escape back into space, or dramatically alter the orbits of both worlds. Placing the moon into a stable orbit would not be like positioning an object and simply letting go. Its velocity would have to be adjusted with extraordinary precision so that gravity could hold it without drawing the two bodies into a collision. If such an event had occurred during the age of humanity, tides across the entire planet would have changed almost immediately. Coastal regions would have faced an entirely new rhythm of rising and falling water, while ecosystems dependent on the tides would have undergone a major disruption. Earth's rotation would also have been affected. The moon and our planet continuously exchange angular momentum through the tides. The sudden arrival of a large satellite would have created stress within the crust and changed the length of the day. Coastal sediments, fossils, and traces of organisms adapted to tidal cycles should have recorded such an event in many places around the world. Yet geology reveals no recent moment when Earth's entire tidal rhythm suddenly began. Instead, lunar rocks and models of solar system formation indicate that the moon has existed for about 4.5 billion years. It appeared very early in Earth's history, long before complex organisms, humans, or any civilization came into existence. The difference between 4.5 billion years and a few thousand years is not a minor discrepancy. If the moon's entire history were compressed into a single day, civilizations with writing would appear only within the final tiny fractions of the last second. Ancient legends were therefore recorded far too late to be direct memories of the moon's formation. This does not diminish their value, but it makes a literal astronomical interpretation difficult to reconcile with the physical evidence. Some stories also connect the moon's appearance with a great flood. The satellite is placed in the sky, the seas rise, and the old world is submerged. This connection may sound reasonable because the moon truly does influence the tides. If ancient people recognized the relationship between the lunar cycle and the water level, they may have imagined that the arrival of a new moon had pulled the sea across the land. But great flood legends appear in many places, even when the moon is not mentioned. One reason may lie in the places ancient people chose to live. Early communities often settled near rivers, lakes, and coastlines. Water provided food, transportation, and fertile soil. But it also brought the danger of floods, large waves, and sudden changes in the shoreline. A river overflowing its banks could destroy the entire world known to a community. Homes, fields, and loved ones might disappear within hours. To the survivors, it truly would have been a flood that swallowed everything. As the story passed through generations, the scale of the disaster could expand. A flooded valley became an entire land beneath the water, and that land gradually became the whole world. Beyond local floods, people living near the end of the last ice age also experienced a period of dramatic coastal change. About 20,000 years ago, global sea level was roughly 125 meters lower than it is today, because an immense amount of water was trapped in continental ice sheets. Beginning around 15,000 years ago, the great ice sheets started to retreat, and sea levels rose. By about 8,000 years ago, the ocean had approached its present level, submerging many plains, valleys, and former coastal settlements. This rise did not occur as a single wall of ocean sweeping across the planet, but over the lives of many generations, shorelines steadily moved inland, and places that had once been inhabited gradually disappeared beneath the water. In some regions, tsunamis, collapsing glacial lakes, or sudden changes in river courses may have made the process far more violent. Local disasters of this kind were powerful enough to survive in communal memory for a very long time. This may help explain why distant cultures independently developed stories of great floods. They did not necessarily preserve memories of one global event, but may have been describing different disasters that occurred in similar environments. Legends can therefore sometimes preserve fragments of real memory. Stories of rising water, awakening volcanoes, shaking ground, or stones falling from the sky may have begun with events that truly happened. Researchers have sometimes used oral traditions about earthquakes and enormous waves as clues in the search for geological evidence. But to become scientific evidence, the story must still be compared with rocks, sediments, archaeology, and reliable dating. If a legend describes fire falling from the sky, researchers can search for a crater, layers of melted material, or fragments of a meteorite. If the story speaks of the sea rising, coastal strata may reveal when the water arrived and where it came from. A symbolic image cannot replace a physical measurement. The phrase, "the moon was born," is not enough to determine whether it refers to the satellite's actual formation, a new moon, an eclipse, or the birth of a lunar deity. Science requires traces that can be measured, tested, and independently compared. Mythology works differently. It does not necessarily attempt to record the distance, mass, or orbit of a celestial body. Ancient stories often used the sky to speak about human life. The moon might represent a mother, someone who had died, the cycle of life, change, or a promise to return. When the moon disappeared and then returned, it became a symbol of rebirth. When the same moon could be seen from distant lands, it became a connection between people living far apart. Those meanings are no less valuable simply because they are not astronomical data. They show that human beings observed the moon long ago, recognized its cycles, and carried the changing sky into their collective memory. Science and mythology may begin with the same curiosity, but they follow different paths. Myth asks what the moon means to human beings. Science asks what it is made of, how it moves, and what physical traces it has left behind. One path searches for meaning, the other searches for mechanism. When the two are confused, A symbol can be mistaken for a technical report, but when placed in the proper context, mythology can still help us understand how distant generations experienced the sky and faced changes they could not yet explain. For most of history, humans could not travel to the moon to test these stories. The far side remained completely invisible, while the dark regions on the surface could be studied only with the naked eye or through limited telescopes. The questions therefore survived in poetry, legend, and oral tradition. The moon could be a god, an egg, a chariot, or an object placed in the heavens. When the space age began, the language of mystery also changed. Gods were replaced by extraterrestrial beings. Celestial chariots became spacecraft. Omens gave way to photographs, radio signals, and interrupted recordings. More than 2,000 years after the story of the Arcadians who existed before the moon was written down, humanity could finally fly around that world and enter the region that could never be seen from Earth. In May 1969, Apollo 10 carried Thomas Stafford, John Young, and Eugene Cernan into lunar orbit to rehearse nearly the entire landing procedure. When the spacecraft passed around the far side, the moon itself blocked direct communication with Earth. During that period of silence, the three astronauts heard a thin, high-pitched sound coming through the radio system. It did not resemble the voices of mission control, nor did it sound like anything that could travel through the vacuum outside the spacecraft. Ancient legends cannot prove that the moon was once absent, but in 1969, questions about that world no longer existed only within mythology. They had appeared on an audio recording, while three human beings traveled across the far side of the moon and described what they were hearing as a strange kind of music from outer space. Ancient legends cannot prove that the moon was once absent from the sky, but when humans began traveling there, the questions no longer existed, only in stories passed down through generations. They appeared in photographs, radio signals, and recorded conversations drifting through space. In May 1969, Apollo 10 entered lunar orbit. It was the final rehearsal before humans attempted an actual landing, carrying out nearly every stage of a lunar descent except the moment of touching the surface. The three astronauts, Thomas Stafford, John Young, and Eugene Cernan, traveled farther from Earth than any ordinary journey could ever reach. As the spacecraft passed behind the moon, their home planet disappeared from view, and the voices from mission control suddenly fell silent. This loss of communication was not an accident. The moon's body, thousands of kilometers across, stood between the spacecraft and Earth, blocking direct radio transmission. Mission control knew exactly when the signal would disappear and when the spacecraft was expected to emerge again. But for the people aboard, that silence carried an entirely different feeling. There was no voice from Houston, no immediate response, and no way to call for help if a serious problem suddenly arose. Before them stretched the cratered far side, a landscape that no human had seen with their own eyes until only a few years earlier. Behind them, the moon concealed the entire Earth. For those minutes, the three astronauts were temporarily separated from the rest of humanity. Then, within that isolation, a strange sound appeared in their headsets. It was not a loud explosion or a clearly recognizable voice. The sound was thin, high-pitched, and wavering, sometimes resembling a whistle and sometimes like a radio signal sliding across several frequencies. The astronauts noticed it immediately. In the recorded conversation, they discussed what they were hearing and described it with a phrase that easily captured the imagination, a kind of outer space music. That phrase was later separated from its original context and spread widely. Some accounts claimed that the crew had heard a signal coming from the far side of the moon, where a base or equipment belonging to an unknown civilization was said to exist. Other versions insisted that the sound continued throughout the entire period of lost communication, as though a hidden transmitter operated only when Earth could no longer listen. The mission's expected silence became the perfect setting for a story about something being concealed. The first important distinction is that the sound was real. It was not a fabricated recording created many years later. The Apollo 10 crew genuinely heard and discussed an unusual radio signal, but the appearance of a sound they did not immediately recognize does not mean it came from outside the spacecraft. Electronic systems can produce very strange signals when devices operate near one another or transmit on frequencies capable of interfering. Apollo 10 consisted of two main sections communicating with each other: the command module and the lunar module. Each had its own radio system, designed to keep the crew connected when the two spacecraft separated. When both transmitters operated at the same time, signals from the two systems could mix together. This interference could create a high-pitched sound that shifted with frequency and sounded completely unlike ordinary speech. The phenomenon did not require a source on the lunar surface. It could arise within the communication system itself, much like the squeal or howl produced when two audio devices interfere with one another. The astronauts had been trained to recognize many kinds of spacecraft noise, but Apollo was still an extraordinarily complex system. A particular combination of equipment operating under specific conditions could produce a sound they had never encountered during simulations on Earth. The fact that the signal appeared while the spacecraft was behind the moon also does not necessarily mean the moon was its source. During that period, the modules communicated through internal radio channels, while direct contact with Earth was blocked. The change in communication configuration may have made the interference more noticeable. When the spacecraft returned to the near side and communication with the ground resumed, the electronic conditions also changed. Another question often raised is whether the moon can naturally produce radio signals. It does not possess a strong global magnetic field like Earth, but that does not mean the environment around it is completely free of electromagnetic activity. Some regions of the surface still preserve localized magnetism within the rocks. These may be remnants of an ancient magnetic field or traces created by major impacts. The solar wind also continuously carries charged particles through the space surrounding the moon. However, a sound within a radio system does not require a global magnetic field to form. Transmitters, receivers, electrical cables, and signal processing equipment can all generate interference when frequencies interact in an unexpected way. Radio interference may not feel as mysterious as a transmission from the far side, but it matches the kind of sound that was recorded and does not require the existence of a hidden device on the surface. The important point is that an unusual sound does not automatically become a message. To be considered an intentional signal, it would need to contain repeating structure, information that could be decoded, or a source that could be identified through several independent measurements. The Apollo 10 audio does not contain those elements. It is a genuine signal, but the available evidence is more consistent with interference from the spacecraft's communication system. Even so, the story did not end with the whistle in the astronauts' headsets. As the Apollo missions became part of history, new accounts began to emerge about what the crews were said to have seen. Some rumors were attributed to Neil Armstrong during Apollo 11. They described enormous objects standing near craters, spacecraft arranged in rows, and a secret communication channel used to report what was happening without the public being able to listen. One version claimed that Armstrong said the astronauts were being watched. Another said that beings had already been present on the moon before humanity arrived and warned the Apollo crews never to return. These statements are often presented as conversations that NASA removed from the public broadcast. However, no reliable official mission recording confirms that they were ever spoken during the flight. Many of the rumors appeared only long after the event. They were repeated in books, articles, or accounts from people who had not been part of the mission's communication network. With each retelling, the story often became more detailed. An object of uncertain shape became a spacecraft. A pause in conversation became a secret transmission. An ordinary remark expanded into a warning about extraterrestrial beings. If a conversation had truly been transmitted through Apollo's radio network, NASA would not have been the only organization capable of receiving it. Tracking stations and radio enthusiasts around the world also monitored the missions, including those in countries directly competing with the United States. During the Cold War, the Soviet Union had a powerful incentive to uncover any deception within the Apollo program. If an extraterrestrial encounter had been transmitted over an ordinary radio channel, keeping it completely secret from rival nations would have been extremely difficult. This does not prove that every piece of information was released immediately. Military and aerospace missions can still withhold sensitive data, but an extraordinary claim involving alien spacecraft would require support from original recordings, technical data, or multiple independent witnesses. The words attributed to Armstrong do not meet that standard of evidence. They remain rumors, not confirmed parts of the official mission record. Another feature often mentioned is the presence of gaps in Apollo video or audio transmissions. Whenever a broadcast was interrupted, viewers could easily wonder what had happened during the missing minutes. But not every gap had the same cause. When a spacecraft passed behind the moon, the loss of communication was a direct result of geometry. Radio waves could not travel through the entire mass of lunar rock to reach Earth. The silence began and ended according to the spacecraft's predicted orbital position. At other times, the crew might switch communication channels, transfer between tracking stations, or use a link reserved for technical data. A segment that did not appear in the public broadcast does not mean that every instrument stopped recording. The technology of the time also had severe bandwidth limitations. Images, voices, medical readings, and spacecraft telemetry all had to pass through systems far less capable than modern communication networks. Video was not always transmitted continuously. A camera had to be turned on, aimed correctly, and connected to the transmission system. During many critical stages, technical data and voice communication took priority over images intended for viewers on Earth. A signal could weaken when an antenna was not pointed precisely, when the spacecraft changed orientation, or when one ground station prepared to hand tracking responsibility to another. Interference, recording failures, and the poor quality of later copies could also create missing sections. A gap in the data therefore tells us only that complete information is unavailable for that moment. It does not reveal whether anything was deliberately removed. To demonstrate a cover-up, it would be necessary to show that the data once existed, that someone intentionally erased it, and that the missing material concerned the event being claimed. Silence or a dark screen alone cannot establish all three. Images of the astronauts after the missions have also been used to reinforce suspicion. During some press conferences, they appeared tired, smiled very little, and did not display the excitement many people expected from those who had just walked on another world. From those expressions, some concluded that the astronauts were concealing a frightening event. Certain accounts suggested that their tension came from an encounter they had been forbidden to reveal. The astronauts' condition can be explained by far more immediate factors. They had just completed a mission in which even a minor mistake could have prevented the entire crew from returning home. For days, they lived inside a confined space, slept very little, followed an exhausting schedule, and remained under constant pressure to perform every procedure with absolute precision. After returning, they still had to undergo medical examinations, quarantine, and a long series of interviews. Most Apollo astronauts were military officers or test pilots. They had been trained to control their emotions, report events concisely, and avoid exaggerated reactions during dangerous situations. A person can be exhausted, overwhelmed, and still appear almost completely calm. A brief video clip is not enough to determine whether someone is concealing fear, disappointment, or an encounter with extraterrestrial beings. Along with their words and expressions, strange objects in Apollo photographs also became the source of many theories. A bright point outside a window could be interpreted as a spacecraft. A small object drifting near the module could appear to be something enormous in the distance. In space, distance is extremely difficult to judge with only one camera. There are no trees, buildings, or familiar horizons to provide a sense of scale. A small fragment close to the lens can cover a large portion of the frame. Spacecraft also release small objects continually. Pieces of insulation, flakes of paint, protective covers, or material from spent rocket stages may drift near the vehicle before slowly moving away. Wastewater and water vapor can freeze into tiny crystals when released into space. When sunlight strikes them, they may flash brightly and then disappear, creating the impression of an object accelerating or suddenly changing direction. Reflections on a spacecraft window can also overlap with the view outside. A light source inside the cabin may produce a faint image that makes viewers believe an object is floating beyond the spacecraft. Dust on film, scanning defects, and damaged pixels can create additional shapes that were never present in the actual scene. If something appears in only one frame, shows no continuous movement, and is not detected by another instrument, its true nature can be extremely difficult to determine. The word unidentified is often mistakenly understood to mean extraterrestrial. But those two ideas are not the same. An unidentified object simply means that the observer did not have enough information at that moment to determine what it was. It may have been debris, a reflection, an optical effect, or a familiar object viewed under unusual conditions. Determining its origin would require information about its distance, size, direction of travel, and speed. It would need to be observed from several angles or tracked across multiple frames. Its light spectrum could help distinguish metal, rock, ice, and gas. A single point of light provides none of this information. Being unable to explain it immediately does not transform it into evidence of another civilization. But unusual observations do not need to be dismissed or mocked either. An unexpected piece of data is still worth examining. Many scientific discoveries began with a signal that did not match what researchers had predicted. The difference lies in how conclusions are reached. Science keeps an object within the category of unidentified until more evidence becomes available, rather than immediately choosing the most dramatic explanation. When the Apollo program is viewed as a whole, rumors often receive more attention than the enormous body of physical evidence the missions actually left behind. 6 missions successfully landed humans on the moon. Each landing site provided rocks, soil, and data from a different region, although all of them were still located on the near side. The astronauts returned with a total of about 382 kilograms of samples. Those materials were distributed among many laboratories and continue to be studied with technologies that did not exist when they were collected. If the entire moon were a manufactured structure, the samples should contain traces of that process. Instead, they reveal minerals, histories of melting and impact, and formation ages consistent with an ancient rocky world. Apollo also left seismometers behind, which recorded moonquakes, meteorite impacts, and deliberately controlled crashes. The data helped scientists construct models of the moon's crust, mantle, and small central core. Laser reflectors still allow the distance between Earth and the moon to be measured. Through them, we know that the moon is moving away from us by only a few centimeters each year. Thousands of photographs document the surface, the equipment, the astronauts' paths, and their activities. Many hours of conversation and technical data allow most of the missions to be reconstructed in extraordinary detail. This evidence does not make every question disappear. The far side has not been fully sampled. Many polar regions remain unexplored at close range, and the deep interior still requires new seismic networks. But it creates a serious problem for the idea of a complete cover-up. If the moon were a gigantic machine or artificial structure, secrecy would require far more than the silence of a few astronauts. It would have to involve generations of engineers, geologists, orbital specialists, and data analysts. NASA is not the only organization to have observed the moon. Many countries have sent flyby spacecraft, orbiters, landers, and rovers there. Some were once direct rivals in the space race. Independent observatories and researchers also track the moon's motion, its orbit, gravitational field, and influence on Earth cannot be altered within a single database. A planetary-scale, artificial structure would have to leave traces in its mass, density, moment of inertia, seismic behavior, and materials. Concealing all of them would require every independent research group to produce the same false results over many decades. That scenario becomes increasingly complicated as the number of missions grows. Every new spacecraft adds cameras, radar, spectrometers, and gravitational data collected by another agency. A major hypothesis should not be rejected simply because it sounds difficult to believe. But the scale of a claim determines the scale of evidence required. The idea of an artificial moon demands physical evidence far stronger than an unusual sound, an unrecorded story, or an unidentified point of light in a photograph. Apollo 10 really did detect a sound the astronauts described as music from outer space. But radio interference fits the technical system and does not require a hidden transmitter. The Apollo missions really did experience periods of silence, but most resulted from the moon blocking the signal, the limitations of the equipment, and the way the communication links were operated. Apollo photographs really did contain objects that were not immediately recognized, but many of them are consistent with debris, ice crystals, reflections, or imaging defects. No reliable recording confirms that the astronauts saw enormous spacecraft waiting on the surface. The published body of data also shows no evidence that an extraterrestrial encounter took place. This does not make the Apollo journeys any less extraordinary. 3 human beings once traveled behind another world, lost all communication with Earth, and heard a sound they did not recognize. That experience alone lies far beyond almost anything humanity had ever known. But Apollo's greatest value is not found in gaps that can be filled with speculation. It lies in the rocks, measurements, and instruments that continued answering questions long after the astronauts returned home. Those observations do not reveal a moon-concealing spacecraft. They reveal a natural celestial body with a long history of impacts, a fractured crust, a small core, and an orbit that is still slowly changing. Apollo provides no reliable evidence of a civilization watching Earth from the far side. But the moon does not need to be a secret machine to exert a profound influence on our planet. Its gravity still raises and lowers every ocean. Those moving waters pull back on Earth, slowing the planet's rotation by an almost imperceptible amount and transferring energy into the moon's orbit. That influence is not hidden in a rumor or a secret recording. It unfolds every day along every coastline and has continued for billions of years. The moon may not control the human mind, but it truly does govern part of the rhythm of the oceans, change the length of the day, and influence many living creatures that follow the light and the tides. Apollo provides no reliable evidence that the moon is a device monitoring or controlling humanity. But that does not mean our satellite merely hangs silently in the sky without affecting the world below. Even after the moon has slipped beneath the horizon, its gravity continues pulling on every part of Earth. The effect is far too subtle for the human body to feel directly, yet strong enough to keep enormous masses of ocean water moving around the planet. The clearest expression of that pull is the tide. Each day, along many coastlines, the water rises and falls in a relatively steady rhythm. Broad beaches may disappear beneath the sea, harbors change in depth, and rocky shores emerge for only a few hours before the ocean covers them again. This familiar movement is among the most visible evidence that a celestial body hundreds of thousands of kilometers away is still directly influencing Earth. A simple explanation often says that the moon pulls ocean water toward itself, creating a bulge on the side of Earth facing it. This is true, but incomplete, because another region of high tide also forms on the opposite side of the planet. The reason lies in the difference in gravitational pull. The side of Earth closer to the moon is pulled slightly more strongly, while the far side is pulled slightly less. That tiny difference gently stretches the entire planet along the line connecting it to the moon, creating two relative bulges of water on opposite sides. As Earth rotates, coastal regions move through these bulges. This is why many places experience two high tides and two low tides over roughly one day. In reality, however, tides are far more complicated than two stationary bulges on a sphere. Continents block the flow of water. The seafloor varies in depth, and the shapes of bays and narrow channels can amplify or weaken changes in sea level. Along a broad open coast, the tide may produce only a modest change in water level. Inside a narrow bay with the right shape, water can become concentrated and rise by several meters. Friction against the seafloor and continental shores also means that high tide does not occur at exactly the moment when the moon is highest in the sky. Tide tables must therefore be built from years of observation and calculations tailored to each location rather than from the moon's immediate position alone. The moon is the primary cause of Earth's tides, but the sun also contributes. The sun is vastly more massive, yet it is much farther away. For tides, what matters is not only the total gravitational pull, but also how much that pull differs between the two sides of the planet. Because the moon is closer, its tidal influence is stronger, but the sun's pull is still powerful enough to change the rhythm of the water, according to the positions of all three bodies. When the sun, Earth, and moon lie close to the same line, the tidal effects of the sun and moon reinforce one another. This occurs near the new and full moon, causing high tides to rise higher and low tides to fall lower than usual. When the directions of the sun and moon form an angle close to 90 degrees as seen from Earth, their effects partly oppose one another, reducing the difference between high and low tide. These variations can be predicted through orbital motion and gravity without invoking any mysterious form of undiscovered energy. The moon's ability to move the oceans often leads to a familiar thought. Because the human body contains so much water, could the moon create tides within us and alter our emotions, thoughts, or behavior? Physically, the moon does exert gravity on the human body, just as it does on every object with mass. But the existence of a force does not mean that it is strong enough to produce a meaningful biological or psychological effect. The oceans stretch across thousands of kilometers, allowing the difference in gravitational pull between opposite sides to accumulate over an enormous distance. The human body is only a few meters in size, so the difference in lunar gravity between the head and feet is unimaginably small. The water inside us is also not gathered into a freely moving body like an ocean. It is held within cells, tissues, blood vessels, and organs. Biological activity, internal pressure, and Earth's gravity are all far stronger than the moon's tidal influence on such a small scale. Even relatively large lakes show almost no obvious lunar tides because they are so small compared with the oceans. The human body is smaller still and far more tightly contained, so its high water content is not enough to prove that emotions rise and fall with the lunar phases. A person standing nearby also exerts a gravitational force on us, but that force is far too weak to alter our thoughts. The important question is not whether gravity exists, but whether it is strong enough to overcome normal biological variation. Another commonly mentioned connection involves the length of the menstrual cycle and the lunar cycle. A lunar month lasts about 29.5 days, relatively close to the average length of many human biological cycles. This similarity has linked the moon with fertility in many cultures, where the full moon, childbirth, and the rhythms of the body often appear together in symbols and rituals. However, menstrual cycles do not have the same fixed length for everyone. They vary between individuals, across different stages of life, and sometimes from one month to the next. in the same person. If the moon directly controlled these cycles, a clear synchronization should appear across large populations, with their starting times consistently clustering around a particular lunar phase. Current data does not show the entire population following such a rhythm. Some studies have reported coincidences between bodily cycles and lunar cycles in small groups, while others have found no stable connection. Results can vary according to sample size, the duration of observation, and the method used to collect the data. The similarity in timing is interesting, but it is not enough to establish cause and effect. Two rhythms with comparable periods are not necessarily controlling one another. Moonlight can affect daily life indirectly, especially in the centuries before electricity. A full moon night is considerably brighter than a moonless one, allowing people to travel, hunt, or work outside for longer. In communities that depended entirely on natural light, nighttime brightness could influence when people returned to sleep. If sleep changed with the lunar cycle under those conditions, the cause may have been light and behavior, rather than a mysterious force acting directly on the brain. In modern society, light from street lamps, electric bulbs, phones, and screens is usually far brighter than moonlight. Most people sleep indoors beneath roofs and behind curtains, greatly reducing direct exposure to lunar light. Some studies have still reported small changes in sleep duration or quality near the full moon, but others have not observed the same effect or have been unable to reproduce the results consistently. Sleep is influenced by many factors, including stress, temperature, noise, work schedules, health, and the use of electronic devices. When a proposed effect is very small, isolating the moon's role becomes difficult. A reasonable approach is to acknowledge that natural moonlight may influence nighttime activity in certain environments, while recognizing that there is not enough evidence to conclude that the full moon directly controls melatonin or sleep in everyone. The belief that the full moon makes people behave unusually has existed for a very long time. In many cultures, the moon has been associated with losing control, shifting moods, and unpredictable behavior. Hospital workers, police officers, and people working night shifts sometimes report that their shifts under a full moon seem more chaotic. These stories feel persuasive because they are connected to real experiences, but human memory does not preserve every night equally. A strange event occurring beneath a full moon is easy to remember and retell because the bright lunar disk becomes a vivid detail in the story. An entirely ordinary full moon night is quickly forgotten. If the same incident happens during another lunar phase, few people check or remember the moon's position. This is confirmation bias, in which people notice cases that support an existing belief while overlooking the many cases that do not. To determine whether the full moon truly increases crime, accidents, or hospital admissions, researchers cannot rely on a few memorable shifts. They must examine data collected over long periods and across many locations, while also controlling for factors such as the day of the week, season, weather, festivals, alcohol use, and social conditions. Large-scale studies generally do not show a consistent connection between the full moon and increases in crime, surgical complications, or mental health emergencies. This does not mean that every study produces exactly the same result. When many datasets are examined, a few random associations will inevitably appear. But unless an effect can be reproduced consistently in independent studies, it cannot yet be considered a natural law. A coincidence may create a compelling story, but that story must still be tested against a much broader body of evidence. The moon does not need to act directly on the human mind to influence life. Many animals truly adjust their behavior according to moonlight, the tides, or a combination of both. In the ocean, some organisms synchronize their reproduction with the rising and falling of the water, allowing eggs and sperm to be released at nearly the same time. Across such a vast environment, This synchronization can greatly increase the chances of successful reproduction. Some coral species reproduce almost simultaneously on particular nights of the year. Light, water temperature, season, and the lunar cycle all help determine this complex timing. Many fish, crabs, and other creatures living in tidal zones also adjust their feeding, hiding, or movement according to the water level. For them, the moon is not a distant symbol, but part of an environmental clock. On land, moonlight changes the relationship between predators and prey. Bright nights help some animals see more clearly, but also make them easier to detect. Small animals may become less active during a full moon to avoid predators, while hunters that depend heavily on vision may use the additional light to find food. The effect is not the same for every species, because each animal uses light, sound, scent, and vibration in different ways. These are ecological influences that can be observed and measured. They arise from light, tides, and environmental change, not from evidence that the moon is transmitting a secret signal. The fact that one organism responds to moonlight does not mean every species is controlled in the same way. Each effect must be considered within the specific biological context of that species. Some hypotheses go further, describing the moon as an enormous transmitter capable of altering human consciousness. According to these ideas, reflected moonlight has been filtered, encoded, or modified before reaching Earth. In reality, moonlight is primarily sunlight, reflected from the dust and rock on the lunar surface. Its spectrum can be measured, revealing how different minerals absorb and reflect different wavelengths. There is no reliable evidence that this light contains a code designed to control consciousness, nor is there any measured physical mechanism showing how a signal from the moon could act simultaneously on billions of brains. Words such as energy, frequency, and quantum are often used in these hypotheses, but scientific terminology does not become evidence simply because it is placed beside a mysterious claim. All light has a frequency. The body constantly uses energy, and matter at very small scales follows quantum mechanics. Those general facts do not imply that the moon is a mind-control device. Demonstrating such a mechanism would require identifying the signal, measuring its intensity, explaining how it interacts with neurons, and showing that the effect can be reproduced under controlled conditions. So far, no reliable data has met those requirements. The moon's confirmed influences are simpler, but no less profound. The tides continually create unique coastal environments where organisms must adapt to being submerged in water at one moment and exposed to air at another. These regions undergo repeated cycles of dryness and moisture, along with changes in temperature, salinity, and nutrient availability. The moon is not the sole cause of life, but it has helped shape the environments in which life on Earth has evolved over billions of years. Tides also mix water, transport nutrients, and influence coastal currents. These effects repeat so gradually that people often regard them as an ordinary part of the world. Yet behind every rise and fall of the sea is an exchange of energy between Earth and the moon, a process that is changing the motion of both bodies. Earth rotates faster than the moon travels around its orbit. Because of friction between the oceans, the seafloor, and the continents, the tidal bulges do not remain perfectly aligned with the moon. Instead, they are carried slightly ahead of it. The gravitational interaction between the moon and these displaced bulges transfers part of Earth's rotational momentum into the moon's orbit. As a result, Earth's rotation slows by an extraordinarily small amount, causing the length of the day to increase gradually over time. In the distant past, the planet rotated faster, and each day was shorter than it is now. The energy transferred to the moon expands its orbit, causing the satellite to slowly move farther away from Earth. This process unfolds far too slowly to be noticed while standing on a beach. No individual tide can reveal that the moon has moved slightly farther away, but billions of tiny motions accumulated over time have carried it from a much closer orbit in the past to its present distance. The moon may not control human emotions, thoughts, or decisions, but it truly does move the oceans, help shape coastal environments, and alter the rotational rhythm of the entire planet. Its greatest influence is not found in a strange night beneath the full moon, but in processes so slow that a human lifetime can witness only a tiny fraction of them. Every time the tide rises and falls, an unimaginably small portion of Earth's rotational energy is transferred into the moon's orbit. Through this process, the familiar satellite in our sky moves several centimeters farther away each year. That distance is insignificant over a night, a year, or a human lifetime, but over hundreds of millions of years, it will make the moon appear smaller in the sky and eventually bring an end to the total solar eclipses that once made humanity feel as though everything had been arranged with perfect precision. Each time the tide rises and falls, a tiny portion of Earth's rotational energy is transferred into the moon's orbit. This exchange unfolds so quietly that no one can see it with the naked eye. Yet over immense spans of time, it continues to change the distance between the two worlds. If the moon truly occupies a perfect position, that position is not fixed. It is merely passing through a remarkable distance along a journey lasting billions of years. The moon's average distance from Earth is currently about 384,400 kilometers. This number does not remain constant at every moment because the moon's orbit is elliptical rather than perfectly circular. During each journey around Earth, it sometimes moves closer and sometimes farther away, causing the size of the lunar disk in the sky to change slightly in ways that are difficult to notice with the naked eye. When the moon is closer to Earth, it appears a little larger and is sometimes given the familiar name supermoon when this occurs near the full moon. When it is farther away, the lunar disk appears smaller. The difference is not great enough to make the moon look like an entirely different object, but it is enough to determine whether a solar eclipse will be total or annular. Beyond the changes that occur during each orbit, the average distance is also increasing over time. The moon does not simply move closer and farther away before returning to exactly the same position. Its entire orbit is slowly expanding, carrying the satellite a tiny amount farther from Earth with each passing year. Humanity can measure this change using laser reflectors placed on the lunar surface. A laser pulse is sent from Earth, travels through space, strikes a reflector, and returns. By measuring the time required for light to complete the journey, the distance between the two worlds can be determined with remarkable precision. Measurements collected over many decades show that the moon is currently moving away from Earth at an average rate of about 3.8 centimeters per year. That is only about the length of part of a finger, far too small to create any noticeable difference within a human lifetime. A person could watch the moon from childhood into old age without seeing it shrink in the sky. But large changes in nature do not always begin with a sudden leap. They are often built from countless tiny movements, repeated continuously. A few centimeters each year may seem insignificant, but accumulated over millions or hundreds of millions of years, they are enough to transform the appearance of the entire sky. The energy carrying the moon into a more distant orbit does not come from an engine or some mysterious force. It comes from Earth's own rotation. Our planet spins on its axis much faster than the moon completes one orbit, and this difference creates an exchange of angular momentum between the two worlds. The moon's gravity produces tidal bulges in the oceans, but because Earth rotates rapidly and the water experiences friction against the seafloor and the continents, those bulges do not remain perfectly aligned with the line connecting Earth and the moon. They are pulled slightly ahead in the direction of the planet's rotation. The moon pulls on the water bulge lying ahead of it, while that water also pulls back on the moon. This interaction transfers some of Earth's rotational momentum into the satellite's orbital motion. As the moon gains angular momentum, it moves into a higher orbit and travels farther away. Earth therefore rotates more slowly by an extremely small amount. The length of a day gradually increases over time, although the change is far too subtle to notice over only a few years. Clocks do not suddenly begin running slower, but on geological timescales, the number of hours in a day is not fixed forever. In the distant past, Earth rotated faster than it does now. A day was shorter, the moon was closer, and it appeared larger in the sky. The tides were also stronger, because the distance between the two worlds was smaller. If we could stand on the young Earth and look upward, the moon would occupy a much larger portion of the sky. Its passages in front of the sun would not create the delicate fit seen today. The larger lunar disk would cover more of the star than necessary, possibly hiding much more of the solar corona. The Earth-Moon system has therefore never been motionless. From the moment it formed, the two worlds have continuously changed their distance, rotational speeds, and influence on one another. Their present arrangement is not the end point of a process, but only a temporary state between a very different past and an equally different future. As the moon continues moving away, its apparent size will gradually decrease. The sun's apparent size also changes slightly because of Earth's orbit, but the long-term trend remains clear. The moon will find it increasingly difficult to cover the entire Sunday. In the far future, a time will come when the moon, even at the closest point in its orbit, will no longer appear large enough to completely conceal the solar disk. Eclipses will still occur, but a ring of light will always remain around the dark moon. Total solar eclipses will disappear, leaving only annular and partial eclipses. The moment when daylight falls into darkness, the temperature drops, and the corona appears around a black circle will no longer exist anywhere on Earth's surface. A phenomenon that once astonished generations will become something known only through images, data, and memories preserved from an age far in the past. This reveals that the moon's apparent perfection is not a condition preserved forever. It was once too close. It now occupies a distance that allows nearly exact coverage, and it will continue moving farther away. Humanity happens to live during a period when the apparent sizes of the moon and sun are nearly equal. Compared with the roughly 4-5 billion year history of the Earth-Moon system, this window is only a relatively brief interval. It is long enough for many civilizations to witness eclipses, yet it remains only one stage in the continuously changing history of these two celestial bodies. If the exchange of angular momentum were to continue forever, another question would arise. Could Earth eventually become tidally locked to the moon, just as the moon now keeps nearly the same side facing us? In theory, Earth's rotation could continue slowing until one turn on its axis took exactly as long as the moon needed to complete an orbit. At that point, the same hemisphere of Earth would always face the moon, while the opposite hemisphere would never see it. The moon would appear almost motionless in the sky above half the planet. In some regions, it could remain suspended in the same position, never rising and never setting. On the other half of Earth, people would live beneath a sky in which the moon was never visible, but reaching that state would require far more time than the present system has left. The sun will continue to evolve, grow brighter, and eventually undergo dramatic changes long before Earth could complete the process of becoming tidally locked to the moon. The true future of these two worlds, therefore, depends on more than the tidal forces between them. It also depends on the evolution of the sun, the loss of Earth's atmosphere, changes in surface temperature, and many other processes unfolding throughout the solar system. Although the moon has been studied through telescopes, orbiters, landers, and rock samples, many scientific questions remain unresolved. The precise details of the collision that created it are still being debated and refined through new models. No one knows exactly how large Theia was, the angle at which it struck Earth, or the speed of the impact. There is also no final answer for how much of the moon's material came from Earth and how much came from the impactor. The isotopic similarity between the two worlds remains one of the key challenges that current models must continue to address. The process by which the moon gathered together after the collision is also not understood in every detail. A large portion of the material may have combined very quickly, but the magma ocean needed time to cool. The first crust needed time to form, and later impacts continued to break apart and rebuild the surface. The differences between the near and far sides still contain many unanswered questions. The far side crust is thicker, while the near side contains more lava plains and heat-producing element. Some models explain part of this asymmetry, but no single explanation yet accounts for all the available data. The deep thermal structure beneath the mantle has not been fully mapped either. The Apollo seismic network operated only on the near side and within a limited region. New instruments placed on the far side and near the poles may reveal a core, mantle, and partially molten zones that differ from current models. The history of water on the moon is also more complicated than scientists once believed. A world once considered completely dry has turned out to contain water within minerals and ice in permanently shadowed regions. That water may have come from the interior, meteorites, comets, or several processes acting together. Regions that have never been sampled may preserve material from very different eras. The far side may contain ancient crust that was never covered by lava, while the polar regions may hold volatile substances accumulated over immense spans of time. Much also remains unknown inside lunar lava caves. These underground tubes may extend for kilometers, protecting material from radiation and extreme temperature changes. They may become shelters for future explorers while also preserving parts of the moon's geological history that have remained undisturbed beneath the surface. These mysteries are real. They do not need to be exaggerated into alien cities or gigantic machines to be worth exploring. Every gap in the data may contain another piece of the solar system's history. After examining the greatest questions surrounding the moon, we can organize what has actually been observed. The moon has an apparent size close to that of the sun and creates total solar eclipses with an almost perfect fit. This is a real phenomenon, explained by the sizes and distances of the two celestial bodies. The moon keeps nearly the same hemisphere facing Earth. This is also true, but the cause is consistent with tidal locking, a natural process found among many other moons in the solar system. Some lunar vibrations really do last longer than earthquakes on Earth. However, seismic data shows that this is related to the moon's dry, cold, and heavily fractured crust, not evidence of an artificial hollow chamber. Gravitational anomalies also truly exist. These mass concentrations once altered spacecraft orbits, but they are consistent with impact basins, uplifted mantle material, and basaltic lava rather than a mechanical outer shell. The near and far sides differ clearly in terrain, crustal thickness, and volcanic history. The complete origin of this asymmetry is still being studied, but tidal locking itself is not evidence that the far side was deliberately hidden. Apollo 10 truly recorded an unusual radio sound while passing over the far side. The astronauts really did describe it as a kind of outer space music. Yet interference between the communication systems provides a more plausible explanation than an extraterrestrial transmitter. The moon is also truly moving away from Earth. Laser measurements confirm that the average distance increases by about 3.8 centimeters each year, because angular momentum is transferred from Earth's rotation into the moon's orbit. All of these phenomena are remarkable, but there remains an enormous distance between these real observations and the conclusion that the moon is an artificial structure. There is no evidence that the moon is a hollow sphere surrounding a chamber filled with machinery. Measurements of its mass, density, moment of inertia, seismic behavior, and gravitational field are consistent with a rocky body containing a crust, mantle, and core. There is no evidence that a manufactured metallic shell lies beneath the surface. Regions rich in titanium, uranium, or other elements can all form naturally within magma and minerals. There are no reliable images confirming cities, bases, or enormous artificial structures on the surface. Many shapes once interpreted as towers or walls have been explained by shadows, terrain, low resolution, and imaging defects. No trustworthy official mission recording shows Apollo astronauts encountering gigantic spacecraft or receiving warnings from another civilization. The most famous accounts usually appeared years later and were not accompanied by original data that could be independently examined. There is also no physical evidence that a civilization placed the moon into orbit, turned it into a surveillance device, or used moonlight to control the human mind. A claim of that scale would require corresponding technical evidence, not merely coincidence or gaps in present knowledge. Legends about an age before the moon are also inconsistent with its geological and orbital history. They remain valuable as cultural memory, symbolism, and expressions of how ancient people understood the sky, but they cannot serve as measurements showing that the moon appeared only during the age of humanity. Based on the available data, there is no reliable evidence that the moon is an artificial satellite. Its rock composition, internal structure, history of melting, craters, and orbital motion are all more consistent with a natural celestial body formed very early in the history of the solar system. The giant impact hypothesis does not explain every detail, but it is supported by several independent lines of evidence. The moon's small core, traces of a magma ocean, the depletion of certain volatile substances, its compositional similarity to Earth, and the motion of the two-body system. An incomplete theory does not mean that every alternative explanation deserves equal weight. A gap in scientific understanding does not automatically become evidence of extraterrestrials. It only shows that more data, samples, and better measurements are needed. Curiosity, however, should not be ridiculed. Looking at a familiar phenomenon and asking why it happens can become the beginning of discovery. Unusual questions sometimes force us to examine more closely what had always seemed obvious. What matters is how the search for an answer is carried out. Instead of beginning with a conclusion and selecting only the evidence that supports it, we must begin with observation, test multiple possibilities, and accept that some questions may not yet have complete answers. Once the artificial hypotheses are set aside, the moon's natural history remains strange enough on its own. A collision between two worlds may have created a large satellite. Fragments of molten rock may have gathered into a new celestial body before cooling into a crust thousands of kilometers across. Gravity can synchronize two motions, keeping one hemisphere permanently turned toward Earth. A satellite, many times smaller than its planet, can still move every ocean, slow Earth's rotation, and gradually lengthen each day. Ancient impacts shattered the crust so deeply that the moon can vibrate for long periods like a bell. A world that appears dead is still slowly contracting, producing faults and small quakes beneath the surface. A movement of only a few centimeters each year will eventually bring total solar eclipses to an end. A change invisible within a human lifetime is still enough to make the sky of the future completely different from the sky we know today. There is no consciousness within gravity, collision, or the transfer of heat. These laws do not know that humanity exists. They do not know that we look up at the sky, nor do they attempt to create anything beautiful. Yet their consequences have produced a system in which everything can seem almost deliberately calculated. In the darkened room where this journey began, the moonlight still rests upon the floor. It is no longer in its original position, but has slowly shifted to one side as Earth continues to rotate. Beyond the window, the oceans are still rising and falling. Somewhere else on the planet, the moon is beginning to rise. Over a more distant land, it is slipping beneath the horizon. With every passing second, Earth continues to lose an unimaginably small portion of its rotational energy. The moon receives that angular momentum and moves slightly farther away by an amount too small for any ordinary instrument to detect immediately. No human lifetime is long enough to watch the lunar disk gradually shrink with the naked eye. No one can stand beneath the sky and directly feel that the day has just grown by the smallest fraction. But the motion continues, whether we notice it or not. The moon is not standing still in a perfect position. It is simply passing through a rare stage in the long history of these two worlds. In the past, it was closer. In the future, it will be farther away. Humanity happened to appear at just the right time to see it almost perfectly cover the sun, to recognize the same familiar face across countless generations, and to wonder whether all of this could truly be nothing more than coincidence. Perhaps the greatest question is not who placed the moon in exactly the right position. What is even more astonishing is that natural laws without thought or intention could create a world that makes us feel as though it had been placed there, quietly waiting for humanity to look up.